Hello and welcome to this revision session for AQA A-Level Physics, Paper 1, in the topic of further mechanics on the concept of simple harmonic motion. So in today's revision session, if we've been successful and we've learned today, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write your answers in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising for AQA A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, student prep notes, the textbooks to learn the key ideas of the course. Now, you may wish to make mind maps or write out notes yourself. The second step is to test yourself. Use things like Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then finally, practice exam style questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. Now you may wish to download your own exam past papers to do this. So your 3 steps should really be, firstly, learning the key facts, then testing yourself, and then answering practice examination style questions. So, when we're doing this revision session today, we'll be looking at 2 types of questions. Firstly, general check questions, which are basic questions designed to probe your understanding of the key concepts of the topic. Then secondly, we're going to be looking at assessment point questions, which are past paper examination questions which will mimic the type of questions found in public examinations. So, let's have a go at some of these general check questions. So the first question says, state and justify whether the following oscillations show simple harmonic motion. A basketball being bounced repeatedly on the ground. So pause the video now, then unpause the video when you want to go through your answer. This is not simple harmonic motion, as there is a constant acceleration of gravity towards the ground, but not on hitting the ground and when hit by the player. A guitar string vibrating. So pause the video now, then unpause the video when you want to go through your answer. Right, the answer is yes, it is simple harmonic motion, as the restoring force is directed towards a point and is proportional to the displacement from that point. The next one, a conducting sphere vibrating between 2 parallel oppositely charged metal plates. So pause the video now, then unpause the video when you want to go through your answer. This is not simple harmonic motion, as it travels with a constant acceleration towards each plate and then suddenly reverses its directional velocity on hitting the plate. The pendulum of a grandfather clock. Pause the video now, then unpause the video when you want to go through your answer. Well, this one is simple harmonic motion, as the restoring force is directed towards a point and is proportional to the displacement from that point. A person jumping on a trampoline. So pause the video now, then unpause the video when you want to go through your answer. Now, when the person is not in contact with the trampoline, the restoring force is equal to their weight, which is constant. Now, their value of weight doesn't change even if they jump higher and change their displacement. Now, the restoring force on a person therefore is not proportional to the distance from equilibrium, so therefore it does not fulfill the conditions of simple harmonic motion. Now, the next one is a cuckoo in a cuckoo clock emerges from a fully compressed position to a fully extended position in 1.5 seconds. Calculate the angular frequency of the cuckoo as it emerges from the clock. So pause the video now, then unpause the video when you want to go through your answer. So, how do you answer this question? Well, we know that when we're working out our value here, our angular velocity is equal to 2 pi over t. Now in this case, t is going to therefore be equal to 3 seconds, because one complete oscillation is when it returns to its original position. So it takes 1.5 seconds to go fully out, and then another 1.5 seconds to go fully back in. So it's 2 pi over 3, which is 2.09 radians per second. The next question says, a mass of 55 grams is suspended from a fixed point by means of a spring. The stationary mass is then pulled vertically downwards through a distance of 4.3 centimeters and then released at t equals 0. The mass is observed to perform simple harmonic motion with a period of 0.8 seconds. Calculate the displacement x in centimeters of the mass at time equals t equals 0.3 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing we need to work out is omega. Now omega is 2 pi over t, so it's 2 pi over 0.8, so it's 7.85 radians per second. Now the general equation for displacement in this case is x equals a cos omega t. It's cos because it's starting from maximum displacement. So it's 4.3 cos 7.85 times by 0.3. Remember, it needs to be in radians for this to work. So we get minus 3.0 centimeters. Now the negative value indicates it's displaced on the other direction or the other side of the equilibrium position from the direction on which it started at. The next question says a simple pendulum is released 30 centimeters from its equilibrium position and completes one complete oscillation every 1.5 seconds. Calculate its displacement 6.2 seconds after it was released. So pause the video now, then unpause the video when you want to go through your answer. As in the last question, omega is equal to 2 pi over t, so it's 2 pi over 1.4, so it's 4.5 radians per second. Now as the pendulum was released at its maximum displacement, we use the cosine version of the displacement equation, x equals cos omega t. Pop in all the values and we get minus 0.27 meters. Remember, the minus indicating it's on the other side of the equilibrium position. The next question says a simple pendulum oscillates with simple harmonic motion with an amplitude of 15 centimeters. The frequency of the oscillations is 6.7 Hz. Calculate the speed of the pendulum at a position of 12 centimeters from the equilibrium position. So pause the video now, then unpause the video when you want to go through your answer. So we know in this case we're given frequency, so omega is equal to 2 pi f, so it's 2 pi times by 6.7, so it's 42 radians per second. Now the general equation for velocity or speed is v equals plus or minus omega times by the square root of a squared minus x squared, so it's 42 times by the square root of 0.15 squared minus 0.12 squared, so our answer is 3.8 meters per second. The next question says, a toy bird is suspended on a spring from the ceiling. It's pulled 3 centimeters downwards and upon release oscillates up and down with an angular frequency of 9.1 radians per second. Calculate the magnitude of the velocity of the toy after 3.4 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, as it's being released for maximum displacement, we can use x equals a cos omega t. So it's 0.6 times by cos 9.1 times by 3.4, which equals 0.0533 meters. That is x. So you can then pop that into the equation of v equals omega times by the square root of a squared minus x squared. Pop in all the values there, so we therefore get 0.25 meters per second. The next question says, a pendulum bob is in simple harmonic motion with a period of 0.60 seconds and an amplitude of 5 centimeters. Calculate the frequency of the oscillations and the maximum acceleration of the bob. So pause the video now, then unpause the video when you want to go through your answer. Well, we know firstly frequency is 1 over time period, so therefore f is equal to 1 over t, so it's 1 over 0.6, which is 1.7 Hz. We then know omega is 2 pi over t, so it's 2 pi over 0.6, so it's 10.4 radians. So this allows us to then work out what our acceleration is, where acceleration is negative omega squared x, where we know omega is going to be minus 10.4, and we know that x is 0.050 centimeters into meters. So we get our answer out to be minus 5.5 meters per second squared. The next question says, state the defining equation of simple harmonic motion. So pause the video now, then unpause the video when you want to go through your answer. Well, the defining equation of simple harmonic motion is always the acceleration equation. So the acceleration is equal to negative omega squared x. The next question says, explain what is meant by the negative sign in this equation. So pause the video now, then unpause the video when you want to go through your answer. The negative sign shows that the acceleration is always directed towards the equilibrium position and is in opposite direction to the displacement. This is what makes the motion oscillatory. The next question says, an object undergoes simple harmonic motion with a starting amplitude of 0.10 meters. An angular frequency of omega is equal to 4 radians per second. What is the displacement at time t equals 0.50 seconds? So pause the video now, then unpause the video when you want to go through your answer. Well, we know x is equal to a cos omega t, so we pop in all our values, we can therefore get minus 0.0416 meters. Again, remember, we use cos as we're starting from maximum displacement. The next question says, for an object with an amplitude of a equals 0.15 meters, an angular frequency 6 radians per second, calculate the maximum velocity. So pause the video now, then unpause the video when you want to go through your answer. So maximum velocity is equal to omega a. So that is 6 times by 0.15, so that's 0.90 meters per second. The next question says, for an object with amplitude a equals 0.15 meters and angular frequency is 6 radians, determine the velocity when the displacement is x is equal to 0.09 meters. So pause the video now, then unpause the video when you want to go through your answer. Well, we know v is equal to plus or minus omega times by the square root of a squared minus x squared. So therefore we can pop in all the values and work it through. Therefore we get our answer to be plus or minus 0.72 meters per second. So the following question says, two identical masses oscillate in simple harmonic motion on identical springs. Mass A follows x equals 0.12 cos 5t. Mass B follows x equals 0.12 sine 5t. What is the phase difference between the two motions? So pause the video now, then unpause the video when you want to go through the answer. Right, well, we know that cos and sine link together because we know that cos is going to be ahead of sine by pi over 2 radians or 90 degrees. So therefore it indicates to us that mass B will lag behind mass A by a quarter of a cycle or 90 degrees or pi over 2 radians. The next question says, two identical masses, mass A, which follows x equals 0.12 cos 5t, and mass B, which follows 0.12 sine 5t, which mass reaches maximum displacement first? So pause the video now, then unpause the video when you want to go through your answer. Now, since A uses the cosine function, it will start with its maximum displacement at t equals 0. Now, B is at its 0 displacement at t equals 0, so therefore we know that A must be at maximum displacement first, because it starts there. So let's now have a look at some assessment point questions. The first question says, a mass is suspended from a spring and set into vertical simple harmonic motion. The displacement of mass x from its equilibrium position is given by the equation x equals 0.040 cos 15t. State the amplitude and angular velocity of the oscillation. Include the units in your answer. Determine the period and frequency of oscillation. Show that the acceleration of the mass satisfies the equation a equals minus omega squared x using the given displacement equation. Calculate the maximum velocity of the mass. Determine the velocity of the mass when its displacement is 0.020 meters, and another identical mass is set into simple harmonic motion with a phase difference of pi over 2 radians compared to the first. Write the expression for the displacement of this second mass. So pause the video now, then unpause the video when you want to go through your answer. So in our first question, we can work out from the equation the amplitude and the angular velocity. So from the equation, A will equal 0.040 meters and angular velocity will equal 15 radians per second. We can then say t is equal to 2 pi over omega, so 2 pi over 15, so it's 0.419 seconds. F equals 1 over t, so therefore it works through to be 2.39 hertz. This next one, what we've got to do is we've got to take the equation x equals a cos omega t, differentiate it twice, that gets us acceleration, so it drops out to be minus omega squared a cos omega t. Therefore, we know a is proportional to minus omega squared x, so therefore it is satisfied. We know that the maximum velocity is omega a, so it's 15 times by 0.040, so it's 0.60 meters per second. The velocity just a given point is equal to omega times by the square root of a squared minus x squared. Pop in all the values and we get 0.52 meters per second. Now the last one, we know a phase difference of pi over 2 implies a sine function rather than a cosine function. So therefore we can change the equation to reflect that by saying it's equal to 0.40 sine 15t. The next question says, A small platform oscillates vertically with simple harmonic motion. A motion sensor records the vertical displacement of the platform as a function of time. The displacement is modelled by the equation x is equal to 0.060 sine 12t. State the amplitude and angular velocity oscillation. Determine the period and frequency of the oscillation. Show that the acceleration satisfies the equation a is equal to minus omega squared x using the given displacement equation. Calculate the maximum acceleration of the platform. Determine the velocity of the mass when its displacement is 0.030 meters. Then another platform undergoes identical oscillations but reaches maximum positive displacement 0.25 seconds after the first. Calculate the phase difference between the motions in radians. So pause the video now, then unpause the video when you want to go through your answer. Right, again, we can work out amplitude and angular velocity from the equation. It's 0.060 meters in 12 radians per second. Frequency is going to be equal to omega over 2 pi. So it's 12 over 2 pi, 1.91 hertz. Time is 1 over frequency, so it's 0.524 seconds. Next, we will take x and we will double differentiate it to turn it into acceleration. So we'll differentiate it twice. So it becomes minus omega squared a sine omega t. So therefore, it satisfies the equation a is equal to minus omega squared x. Our maximum acceleration is omega squared a. So it's 12 squared times by 0.060, so it's 8.64 meters per second. Our general velocity equation is omega times by the square root of a squared minus x squared. Pop in all the values and you work it through to be 0.62 meters per second. Finally, what's our phase difference going to be? Well, our phase difference is going to be equal to 2 pi times by the difference in the time periods over the general time period, or the difference in the oscillation, I should say. So it's going to be 2 pi times by 0.25 over the general time period, 0.524. So therefore we get 3 radians. The next question says, a body is moving with simple harmonic motion. State 2 conditions that must be satisfied concerning the acceleration of the body. A mass is suspended from a vertical spring and the system is allowed to come to rest. When the mass is now pulled down a distance of 76 millimeters and released, the time taken for 25 oscillations is 23 seconds. Calculate the frequency of the oscillations. Calculate the maximum acceleration of the mass and calculate the displacement of the mass from its rest position 0.60 seconds after being released. State the direction of this displacement. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to learn the 2 conditions of simple harmonic motion. Acceleration is proportional to displacement, and the acceleration is in the opposite direction to the displacement towards the equilibrium position. Frequency is going to be the 25 oscillations over 23 seconds, because how many oscillations are there per second? 1.1 hertz. The acceleration is equal to omega squared a, or 2 pi f squared times by a. So it's 2 pi times by 1.09 squared times by 76 times 10 to the minus 3 minus 3.6 meters per second squared. Now we can use the cos equation for displacement because it starts at maximum displacement. So therefore you pop in all the values and you get minus 4.31 times 10 to the minus 2 meters. Now because it's a minus, it tells you on the other side of the equilibrium position from when it started. It started when fully pulled down, so therefore being negative means it's above the equilibrium position or moving upwards. The next question says, 150 gram mass was hung from a spring as shown. The spring was extended by 7.5 centimeters. The mass was displaced vertically 3 centimeters from its equilibrium position and then released. The mass oscillated vertically. Explain why the motion of the mass was simple harmonic motion. Calculate the maximum velocity of the oscillating mass, and then explain why the maximum velocity of the oscillating mass decreased over time. So pause the video now, then unpause the video when you want to go through your answer. Right, so why is that simple harmonic motion? Well, there's always a resultant force that is proportional to the displacement from the equilibrium position, and this force and acceleration are always acting towards equilibrium. Now in this next question, we can work out the force, because we know force is mass times by gravity. So when we turn our grams into kilograms, we get 1.47 newtons. We know that the spring constant is equal to the force over the extension. We convert 7.5 centimeters into meters and we get 19.6 newtons per meter. We now know that the time period of a mass spring system is 2 pi times by the square root of m over k. Pop all the values in and we get 0.549 seconds. We know omega is 2 pi over t, so it's 2 pi over 0.49 seconds, so therefore it's 11.4 radians per second. We then know V max is equal to omega times by A, so therefore we work it through to be 11.4 radians per second times by 3 times 10 to the minus 2, which is 0.343 meters per second. Now in the final question, energy is transferred out of the oscillating system and this energy is dissipated to the surroundings because work is being done against these resistive dampening forces. The next question says, a young girl is swinging on a garden swing. You may assume the swing behaves as a simple pendulum. Ignore the mass of the chain supporting the seat throughout the question and assume that the effective air resistance is negligible. Calculate the distance from the top of the chain to the centre of the mass of the girl in the seat. Express your answer to the appropriate number of significant figures. To set her swinging, the girl in the seat would displace from equilibrium and release from rest. The initial displacement of the girl raised the centre of mass of the girl and seat 250 millimeters above its lowest position. If the mass of the girl was 18 kilograms, what was her kinetic energy as she first passed through the lowest point? And calculate the maximum speed of the girl during this first oscillation. So pause the video now, then unpause the video when you want to go through your answers. Right, so in this first one, what do we know? So, how do you answer this question? Well, in the first instance, what you've got to do is you must work out the time period of each oscillation. So when you do this and you work it through, you do 42 over 15, that gives us a time period of oscillation of 2.8 seconds. We can then use our pendulum equation to work out the time period, and well, from the time period to then work out what our length is going to be. Because you know t equals 2 pi over square root, so 2 pi times by the square root of L over G. So therefore we rearrange it, and L is equal to t squared g over 4 pi squared. So it's 2.8 squared times by 9.81 over 4 pi squared. So this tells us that we get our answer of L to be 1.9 meters. Now again, it should be given to two significant figures as you're given information in the question 15 and 42 of two significant figures. Now in our next question, we can say EK is going to be equal to the potential energy because they're going to transfer between each other. So therefore we can say the kinetic energy is equal to the mg delta H. So at that point we can then say it's 18 times by 9.81 times by how far it is up, which is 0.25 meters, so it's 44 joules. We can then say that's also going to be the kinetic energy. So half mv squared is equal to 44.1. So therefore our maximum speed is going to be 2 times by our energy over the mass. So you get 2.2 meters per second. The next question says, a grandfather clock uses a simple pendulum to keep an accurate track of time. The second's hands of the clock moves forward exactly 1 second each time the pendulum moves from A to C, and another second each time it moves from C to A. Determine the length of the pendulum in the grandfather clock that would accurately tell the time. The average gravitational field strength at the surface of the Earth is 9.81 meters per second squared. The pendulum is lightly damped. As a result, the clock needs to be wound up once a week. Suggest one potential cause of light dampening in the pendulum. Explain why dampening does not affect the clock's ability to tell the time. Then a grandfather clock has a pendulum of length as determined in the first part of the question. It's then used to tell the time at the Earth's equator, where g equals 9.78 meters per second squared. The clock was set to exactly the right time at 1800 hours on Monday evening. So determine the time displayed by the clock at 1800 hours the following Monday. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we know t is equal to 2 pi times by the square root of L over G. So we can rearrange that to put L is equal to t squared G over 4 pi squared. We know t, remember it's the time we're going from A all the way back to A, times by G, and we know 4 pi squared, so we get 0.994 meters. Now, what is causing the light dampening? Well, the light dampening is going to be caused by a dampening force causing energy to dissipate to the surroundings. So friction of the pivot's pendulum, the internal friction due to the tension in the string, and air resistance will cause energy to be lost to the system to the surroundings as heat. Now, dampening will not affect the clock's ability to tell time because the time period of an oscillation is independent of the amplitude. Now, the dampener will cause a reduction in the amplitude, but it would not affect the time period of oscillation to change. That's an important idea that you've got to understand from light dampening. It does not affect the frequency and time period. In our next question, we know t equals 2 pi times by the square root of L over g. We worked out L to be 0.994 meters. So we can pop it t in to get 2.00306 seconds. So what that tells us is that for every 2.00306 seconds that passes, the clock moves forward 2 seconds. So by that logic, for every 1.00153 seconds that passes, the clock moves forward 1 second. Now in 1 week, there are 6.04800 seconds, 60 times by 60 times by 24 times by 7. So in this time, the clock will actually move forward 6.03874.52 seconds, which is 925 seconds slower than the recorded time, which is 15 minutes and 25 seconds. So therefore, the time on the clock shown at 1800 hours on the Monday will be 17:44 and 35 seconds, which shows the importance of why clocks always have to be calibrated. The next question says, during the final stage of a wash cycle, an undamped washing machine increases the rotational frequency of the rotating drum from 0 to 1,250 revolutions per minute. The rotating drum has a diameter of 35 centimeters. Calculate the maximum linear speed that the clothes in the washing machine could reach during the final stages of the washing cycle. Between the rotational frequencies of 600 and 900 RPM, the washing machine can be observed to vibrate. The amplitude reaches a peak at 750 RPM. Firstly, explain the shape of the graph shown. Newer models of the washing machine are heavily damped. Describe what you'd expect the amplitude profile to look like in newer models compared to the graph shown. And then dampening is incorporated into the design of many everyday objects. A set of supermarket scales is damped to reduce the variation in weight measurements when food is put on the scales. State and explain the degree of dampening that is most suitable for a set of supermarket weighing scales. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that Vmax occurs at 1,250 RPM. So therefore, the frequency is 1250 divided by 60 to get into seconds, so it's 20.8 hertz. Now, omega is 2 pi f, so we work it through to be omega to be 130.8996 radians per second. Now, we know that the radius of the circle is going to be the diameter divided by 2, so 0.175 meters. Now, V equals omega r, so it's 130.9 times by 0.175, which is 23 meters per second. Now, the graph can be explained as the rotation of the drum forces the washing machine to vibrate at the same frequency. It's a forced oscillator. So as this driving frequency approaches resonant frequency of the washing machine will resonate, gain more and more energy from the driving force, and cause the vibrations to increase in amplitude. Now, the newer model would have a profile which is flatter, which is less sharp, have a much smaller amplitude peak as the resonant frequency, as that's what dampening causes to happen to the oscillation amplitude. Finally, what dampening would you want? You would want critical dampening, as the amplitude of the variation weight measurement will be reduced in the shortest possible time to get back to equilibrium so you can make your measurement quickly. So that brings an end to our revision session today. If we've been successful and we've learnt in today's lesson, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and understand what topics you need to improve upon for A-Level Physics. So thank you so much for watching this revision session on further mechanics on the topic of simple harmonic motion for AQA A-Level Physics, which is part of paper 1. Thank you so much and have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics on the topic of further mechanics, looking at the concept of circular motion. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you complete your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than the right hand side. And in this left hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you're writing full sentences and show the full working out. whilst in the right hand side, in this section write down any bits of information which you find useful or any hints and tips on answering the questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for AQA A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, student prep nooks and the textbook to learn the key ideas of the course. The second step is to test yourself. Use Caboodle, Seneca, the student knowledge checkers to quickly test your own knowledge. Finally, practice exam style questions. Use exam practice books, supervised study books, homework books, workbooks to answer exam questions and mark your own work. So your 3 steps are learn the key facts, testing yourself, and answering past paper questions. So let's have a look at the key facts regarding circular motion. So uniform circular motion is motion in a circle at a constant speed. This implies acceleration is present towards the centre and that a centripetal force is required to maintain the motion. We know the angular speed or velocity is equal to omega, which is equal to v over r, which is also equal to 2 pi f. Now we measure angles in radians. Now 2 pi radians is 1 full revolution or 360 degrees. Now the centripetal acceleration is the acceleration directed towards the centre of the circular path. So A is equal to v squared over r or omega squared r, whilst the centripetal force is the force required to keep an object moving in a circle and it always acts inward. So we know F equals mv squared over r, which is also equal to m omega squared r. So let's have a look at some key check questions regarding circular motion. So to assess your understanding, answer the following questions. Define a radian as a unit of angular measurement. So pause the video now, then unpause the video when you want to go through your answer. 1 radian is the angle subtended at the centre of a circle when the arc length is equal to the radius of the circle. How many radians are there in one complete circle? There are 2 pi radians in one full circle. Convert the following angular displacement into degrees. To convert into degrees from radians, you times by 360 and divide by 2 pi. So pi over 3 times by 360 over 2 pi is 180 over 3 or 60 degrees. A spinning top completes 8 full revolutions before it comes to rest. Express the angle it moves through in degrees. 1 full revolution is 360 degrees. 360 times by 8 is 2880 degrees. A spinning top completes 8 full revolutions before it comes to rest. Express the angle it moves through in radians. So pause the video now, then unpause the video when you want to go through your answer. We know that in 1 full revolution, that's 2 pi radians. So 8 full revolutions of 2 pi radians is 60 pi radians or 50 radians. A spinning hard disk takes 8.33 milliseconds to complete 1 full revolution. Calculate its angular velocity in radians per second. Omega is equal to 2 pi over t. So we do 2 pi over the time period, 8.33 times 10 to the minus 3 is 754 radians per second. So, therefore, calculate its angular velocity in revolutions per second. Now, revolutions per second is another name for frequency. So frequency is 1 over time period, 1 over 8.33 times 10 to the minus 3, which is 120 revolutions per second. A wheel completes 1 full revolution every 0.4 seconds. What is its period and what is its frequency? The time period is 0.4 seconds, the time taken for 1 complete revolution. Frequency is 1 over time period. 1 over 0.4 is 2.5 Hz. An object moves in a circle with a frequency of 3 Hz. Calculate its angular velocity omega in radians per second. We know omega is equal to 2 pi f. So 2 pi times by 3 is 6 pi. So it's 18.85 radians per second. A wheel turns through an angle of 4 pi radians in 2 seconds. Calculate its angular velocity. We know angular velocity is the change in angle over the change in time. So 4 pi radians over 2 is 2 pi radians per second or 6.28 radians per second. A small object rotates at an angular velocity of 12 radians per second. What is its frequency and how many complete revolutions does it make in 10 seconds? So we know frequency is omega over 2 pi. So therefore it's 12 over 2 pi, which is 1.91 hertz. So therefore, the number of complete revolutions is going to be the frequency times by the time. So it's 1.91, the number of revolutions per second, times by 10, 19.1. Calculate the angular displacement in radians of the tip of the minute hand of a clock in 1 second. So pause the video now, then unpause the video when you want to go through your answer. We know that omega is going to be equal to 2 pi over 3,600, 2 pi over t, and there's 3,600. Okay, working it through, okay, for your entire angle, so it's pi over 1,800. So therefore, it's 0.001745 radians per second. The angle is equal to omega times by t, so we get 0.001745 radians. So, calculate the angular displacement in radians of the tip of the minute hand of a clock in 1 minute. Once again, we know omega is equal to pi over 1,800 or 2 pi over 3,600, but then we're now going to multiply by a time of 60 seconds, so therefore becomes 0.1047 radians. Calculate the angular displacement in radians of the tip of the minute hand of a clock in 1 hour. Once again, we know omega is equal to 2 pi over 3,600 or pi over 1,800. We now multiply it by the number of seconds that you work it through, so you do that times by 3,600, so we get 6.2 radians. But the displacement is going to be 0 as it's returned back to where it starts. The next question says, an electric motor turns at a frequency of 50 Hz. Calculate its time period. We know frequency is 1 over time period, or 1 over 50, so it's 0.02 seconds. An electric motor turns at a frequency of 50 Hz. Calculate the angle it turns through in radians in 1 millisecond. So we know omega is equal to 2 pi f, so 2 pi times by 50 is 100 pi, or 314 radians per second. We know that the angle is equal to the angular velocity times by the time, so we multiply this by 1 millisecond, which is 1 times 10 to the minus 3, which is 0.314 radians. An electric motor turns at a frequency of 50 Hz. Calculate the angle it turns through in radians in 1 second. Same as before, omega equals 2 pi f, so equals 314.16 radians per second. The change in angle is omega times by t, so we times that by 1 for 1 second, so it's 314 radians. In the following situation, what is the centripetal force in this situation? Pause the video now, then unpause the video when you want to go through your answer. It is always the centripetal force is the resultant force towards the centre of the circle, in this case 40 newtons. What is the centripetal force in this situation? It is 22 newtons. What is the centripetal force in this situation? 70 newtons. What is the centripetal force in this situation? Remember, it is the resultant force towards the centre of the circle, 70 minus 40, 30 newtons. What is the centripetal force in this situation? It is 80 minus 20 newtons, 60 newtons. What is the centripetal force in this situation? 120 minus 60 is equal to 60 newtons. What is the centripetal force in this situation? It is 10 minus 40, because that's in the opposite direction to the centre of the circle, so it equals minus 30 newtons. What is the centripetal force in this situation? 50 minus 400 is minus 350 newtons. What is the centripetal force in this situation? Once again, we can say the centripetal force is the resultant force towards the centre of the circle, so it is the weight minus the reaction force. What is the centripetal force in this situation? The centripetal force is equal to mg minus r. What is the centripetal force in this situation? The centripetal force is equal to r minus mg. What is the centripetal force in this situation? Remember, the centripetal force is the resultant force towards the centre of the circle. So in this case it is mg plus r. What is the centripetal force in this situation? Well, it is mg plus r plus t. What is the centripetal force in this situation? Well, the centripetal force is T plus R, because they're both towards the centre of the circle, minus mg. What is the centripetal force in this situation? It is T plus R. Now remember, if forces are perpendicular, they don't affect each other. So weight is perpendicular to the centripetal force, so it has no component acting towards it. What is the centripetal force in this situation? It is mg plus r. Remember, once again, if the forces are perpendicular, they do not affect each other. Tension is perpendicular to the centripetal force, so has no component acting towards it. In the following situation, why must there be a resultant force during angular motion? And reference Newton's laws of motion. So pause the video now, then unpause the video when you want to go through your answer. Right, Phobos is constantly changing direction, so therefore constantly changing velocity, so must be accelerating. Now Newton's first law states an acceleration is caused by a resultant force, and only a resultant force, so therefore there must be a resultant force. In this situation, what would happen to Phobos if the gravitational attraction from Mars was switched off? In this situation, Phobos would only have inertia acting on it, so this makes Phobos move off in a straight line at a constant speed, which is tangential motion. If there is only a centripetal force acting on Phobos, why does it not accelerate towards the centre? Well, Phobos is accelerating towards the centre, but inertia, the tendency to move in a straight line at a constant speed, combines with this force to produce circular motion. So circular motion, which we observe, is the combination of the centripetal force acting towards the centre of rotation and inertia. So, define the centripetal force. The centripetal force is the resultant force that acts towards the centre of a circle to keep an object moving in a circular path. Why is the centripetal force always perpendicular to the velocity of the object? The object moves in a circle at a constant speed, so its velocity vector changes continuously. The centripetal force is perpendicular to the velocity, causing a direction change, but not changing the magnitude of the speed. A car is moving at a constant speed around a circular track. Is it accelerating, and why? Yes, it is. Even though the speed is constant, the direction of the velocity is constantly changing. Since acceleration is the rate of change of velocity, the car must be undergoing a centripetal acceleration. An object moves at a speed of 4 meters per second in a circular path of radius 2 meters. Calculate the centripetal acceleration. So we know A is equal to v squared over r. We know v is 4. We know r is 2. 4 squared over 2 is 8 meters per second. A 0.5 kilogram ball is swung in a circle of radius 1.2 meters at a constant speed of 3 meters per second. Calculate the centripetal force acting on the ball. We know F is equal to mv squared over r. So 0.5 times by 3 squared over 1.2 is 3.75 newtons. A stone of mass 2 kilograms is tied to a string and rotated in a circle of radius 0.75 meters with an angular velocity of 5 radians per second. Calculate the centripetal force using angular velocity. Here we've got to use the equation F is equal to m omega squared r because we don't have v. So we go 2 times by 5 squared times by 0.75 is 37.5 newtons. A car is being driven in a circle of radius 56.8 meters with a linear speed of 31.1 meters per second. Calculate the centripetal acceleration of the car. We know centripetal acceleration is v squared over r, so it's 31.1 squared over 56.8, so it's 17 meters per second squared. On a ride of a theme park, riders are strapped into seats attached to the edge of a horizontal wheel of diameter 8.5 meters. The wheel rotates 15 times per minute. Calculate the force felt by the rider of mass 60 kilograms. Well, we can work out that the frequency is the number of rotations every second, so therefore it must be 15 divided by 60 to get the minutes into seconds, so it's 0.25 hertz. Our angular velocity or speed is 2 pi f, so we go 2 pi times by 0.25 is 0.5 pi radians per second. We've got our angular velocity, so we can use the F equals m omega squared r equation to get our answer to be 630 newtons. Now, a car is being driven in a circle of radius 56.8 meters with a linear speed of 31.1 meters per second. If the linear speed of the car decreased to half of its original value and the original centripetal force produced was F, what is the new value of the centripetal force in the terms of F? So, pause the video now, then unpause the video when you want to go through your answer. So F is equal to mv squared over r. This tells us that if v is halved, then the centripetal force will be quartered, so therefore it is F over 4. A student is investigating circular motion using a whirling bung. She attaches a washer of mass 310 grams to the end of the string and spins a bung of mass 22 grams in a circle of radius 0.60 meters. Calculate the time period of the bung's motion. So we know the weight of the washer is mg, so we turn our grams into kilograms and we get 3.0411 newtons. That's our centripetal force acting on the bung. We've got our angular velocity, because we can work that through. We've then got our radius and we've got our mass. So therefore we can work that through to get our angular velocity. So therefore we can say that equals 3.0411 newtons. Work it all through, we get 15.2 radians per second. We then know t is equal to 2 pi over omega, rearranged in our previous equation, so we get 0.41 seconds. A biker rides in a vertical circle around the inside of a cylinder of radius 5 meters and he is upside down at the top of the cylinder. For the biker to not fall off at the top of the loop, he must be going fast enough so his centripetal acceleration does not drop below the acceleration due to gravity. What is the minimum speed he must be travelling at the top of the loop? If the biker's speed is the minimum possible speed for them not to fall, well therefore our centripetal acceleration towards the centre at the top of the cylinder will equal 9.81 meters per second due to gravity. The bike would fall if the centripetal acceleration is smaller than this. So we can say A equals v squared over r, so v is the square root AR, where A must be 9.81. So we work it through to be 7 meters per second or 16 miles per hour. So let's have a look at some longer questions regarding circular motion. In our first question, a small robotic spacecraft is being tested in a laboratory. It is designed to rotate steadily about its centre using small thrusters to control its motion. A solar panel is attached to the spacecraft and rotates in a circle of a radius 0.80 meters. During one test, the solar panel completes 75 full rotations in 2 minutes. Firstly, explain why radians are used as a natural unit for angular displacement in physics. Calculate the total angular displacement in radians made by the panel during the 2-minute test. Calculate the frequency and period of the rotation of the panel, and calculate the angular velocity of the rotating panel. So pause the video now, then unpause the video when you want to go through your answer. In our first answer, how can we work this through? Well, we know that we should be using radians as our natural unit for angular displacement, as they relate the arc length and the radius directly in a circle, using theta is equal to s over r. This leads to simpler mathematical relationships in rotational motion compared to using degrees. We know one full rotation is 2 pi radians, so the total angular displacement is 75 times by 2 pi, or 150 pi. So our angular displacement is 471.24 radians. In our time period, it's 120 seconds. Frequency is 75 over 120, which is 0.625 Hz. Time period is 1 over frequency, pop it through 1.6 seconds. Angular velocity is equal to the change in angle over the change in time, 471.24 over 120, which is 3.93 radians per second. A model satellite dish in a school laboratory is mounted on a rotating platform. The platform spins with a constant angular speed. A student uses a stopwatch to time 40 full revolutions of the dish, which takes 75 seconds. The radius of the dish's circular path is 0.35 meters. Explain why the radian is a more suitable unit than degrees when working with equations involving angular motion. Calculate the angular displacement of the dish in radians during the 75 seconds. Calculate the frequency and period of the rotation and determine the angular velocity of the dish. So, pause the video now, then unpause the video when you want to go through your answer. Remember, radians provide a direct relationship between arc length and radius using the formula theta is equal to s over r. Using radians simplifies rotational motion equations, making them dimensionally consistent and easy to manipulate. We know one full revolution is 2 pi radians, so the full angular displacement is 40 times by 2 pi or 80 pi. 80 pi is 251.3 radians. Frequency is 40 over 75, so it's 0.533 Hz. The time period is 1 over frequency, so it's 1.88 seconds. Our angular velocity is the change in angle over the change in time, 251.3 over 75, 3.35 radians per second. A circular disc is mounted on a low friction pivot in a physics laboratory. The disc rotates steadily with its point on its rim being used to demonstrate rotational motion principles. During an 80-second test, the disc completes 40 full rotations. Explain why the radian is considered a natural unit for measuring angles in rotational motion. Calculate the total angular displacement in terms of radians of the point on the rim during the 80-second test, and then determine the frequency and period of the rotation of the disc. Then, using the results, calculate the angular velocity of the disc in radians per second. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, radians are a natural unit because they relate arc length and radius directly in a circle, using the equation theta is equal to s over r. This simplifies equations in rotational motion, making calculations much more straightforward. One full revolution is equal to 2 pi radians, so the total angular displacement is going to be 40 times by 2 pi, which is 80 radians per second. 80 radians. The frequency is 40 over 80, so it's going to be 0.5 Hz, while our time period is 1 over frequency, which is going to therefore be 2 seconds. Angular velocity is the change in angle over the change in time, so it's 80 pi over 80 seconds, so it's 3.14 radians per second. At a fairground, a rotor ride spins passengers in a vertical circular chamber. The passengers are pressed against the wall as the floor drops away. The ride rotates at a constant speed, and the friction between the passenger and the wall prevents them from sliding down. The radius of the circular wall is 2.4 meters. Each passenger has a mass of 65 kilograms, and the ride completes 1.2 revolutions per second. Determine the magnitude of the centripetal force acting on one passenger. Use your result to assess whether the ride's design provides enough force to keep the passenger firmly against the wall. In order for the passengers to remain safely against the wall after the floor drops away, the vertical frictional force must be large enough to support their weight. Using your previous result, assess whether the available frictional force provided by the rider is likely to be sufficient. Then explain whether the normal contact force in the system is acting vertically or horizontally. Discuss its role in relation to the motion and the frictional force that keeps the passenger in place. So, pause the video now, then unpause the video when you want to go through your answer. In this first one, we know that frequency is equal to 1.2 Hz because there's 1.2 revolutions per second. Omega equals 2 pi f, which is 7.54 radians per second. The centripetal force is m omega squared r, so you work it through to be 8,940 newtons. So this is our normal contact force towards the center of the circle. A high normal contact force increases the frictional force available to resist the gravitational attraction. So the ride will provide sufficient inwards force to maintain safety if the friction is adequate. The normal contact force from the wall provides the friction needed to support the passenger's weight, the centripetal force of 8,940 newtons, and there's also a magnitude of the normal force. Since the required frictional force is only 637 newtons, the weight of the person, the normal force is very large. The design is going to be very safe under normal conditions. Now, the normal force will act horizontally inwards, so towards the centre of the circle. It's providing the centripetal force that maintains our circular motion. Friction will act vertically upwards, it'll oppose the weight, and it'll stop the person from sliding downwards. A prototype vehicle is tested on the surface of the moon, where the gravitational field strength is 1.62 newtons per kilogram. The vehicle has a mass of 2,000 kilograms and travels at 4.5 meters per second around a circular test track of radius 25 meters. The track surface is flat and no banking is present. Engineers want to ensure that the vehicle stays safely on the curved path during the turn without sliding. So calculate the magnitude of the force required to maintain the vehicle's circular path. Identify the force that actually provides the centripetal force in this situation. Explain how this force prevents the vehicle from skidding outwards during the turn. Then evaluate whether the same vehicle will be able to follow the same curved path safely at the same speed on Earth. Support your answer with references to forces that act on the vehicles and any assumptions that you make. So, pause the video now, then unpause the video when you want to go through your answer. Okay, we know F is equal to mv squared over r, the centripetal force. Pop in all the values, we get 1620 newtons. Now, the force acting towards the centre of the circle is the horizontal component of the normal reaction from either the ground or the frictional force. This force will point towards the centre of the circular path, so it prevents skidding by supplying a force opposite to the inertia that will be taking place. On the Earth, the gravitational force is stronger, increasing the maximum available normal force. So this means the surface can supply a larger real force, so the normal or component or the friction, potentially allowing for tighter turns at higher speeds. The same vehicle on Earth therefore will be easily able to maintain the same curve path, assuming the same road and the same tyres are used. A team of engineers is designing a high-speed curved section of a racetrack for a new electric racing league. The curve has a radius of 120 metres. The target design speed for the cars is 42 metres per second. The engineers want to bank the track so that no friction is required to keep a car travelling around the curve at the design speed, so that the angle of the banking need to eliminate the need for friction at the design speed is approximately 55 degrees. One of the engineers argues that the bank in the corner any steeper would make it dangerous for slower moving vehicles. Explain why this could be true. During real world testing, cars often exit the turn at speeds slightly above 42 meters per second. Discuss whether the current banking angle remains effective and whether any additional physical forces are now required to maintain the circular path. Then evaluate how the banking angle would need to change if the radius of the curve was reduced but the same design speed was maintained. So pause the video now, then unpause the video and you want to go through your answer. Right, in our first one, we can say vertically t sine theta is equal to mg. We know horizontally t cos theta is equal to the centripetal force. It's the resultant force towards the centre of the circle, so it's mv squared over r. We can then do t sine theta over t cos theta. We can therefore work out tan theta to be v squared over rg, pop in all the values, and we get tan theta is equal to 1.5. So theta is equal to 56.3. Now, at lower speeds, v squared over r, the acceleration is smaller, so less centripetal force is required. With a steep bank, the gravity pulls the car down the slope, but there's not enough horizontal component of the normal force to balance this. So therefore, friction is now needed to stop the car from sliding downwards off the curve. At speeds above 42 meters per second, the required centripetal force needed will be greater. Now, the bank angle alone no longer provides enough force via the normal component. So friction is now also required to supplement the horizontal component of the normal force. So we know that will be a t cos theta, and prevent the car from sliding up the slope. Finally, if the radius decreases and the speed stays constant, v squared over r will increase, given a greater result of centripetal force being required. So therefore we would need a steeper banking angle to provide this greater inward resultant force without the need of friction. The next question says, a car was travelling in a circular path as shown. A passenger in the car made the following claim. When the car was travelling at high speed around the circular path, I was thrown outwards due to a force acting on me. The upwards force acting on me was the centrifugal force. Assess the claim made by the passenger. So, pause the video now, then unpause the video when you want to go through your answer. Right. The application of Newton's first law to the path of the car and the passenger indicates that if there was no force, the car and the passenger will continue in a straight line. So you need a resultant force to cause a change in direction. A force was exerted on the car and passenger towards the centre of the circle. That's an inwards force exerted at right angles to motion. This is the centripetal force. Now the inward force is exerted by the car onto the passenger. There is no outwards force. The centrifugal force does not exist. So the passenger's claim is incorrect. The following photograph shows children on a roundabout in a playground. The roundabout is a flat platform with bars. The children made the platform rotate by running on the ground whilst pushing on the bars. It takes 12 seconds for the roundabout to make 2 complete revolutions. A child is standing on the platform 1.8 meters from the centre of the roundabout. Calculate the speed of the child. So, pause the video now, then unpause the video and you want to go through your answer. Okay, we know omega is equal to 2 pi over t. So therefore we know that 1 revolution is 6 seconds, because 12 seconds for 2 revolutions. So 2 pi over 6 is 1.05 radians per second. V is equal to omega r, so therefore we multiply that by 1.8 and we get 1.89 meters per second. A poi ball is attached to a person's hand by a cord. A child makes the poi ball undergo circular motion in a vertical plane as shown in the photograph. The poi ball moves clockwise in a circular radius r with a center 0 with a constant speed v. The diagram shows two positions A and B of the poi ball. Firstly, derive the equation for the centripetal acceleration of v squared over r by considering the velocity of the poi ball at these two positions. Your answer should include a vector diagram. The poi ball completes 1.3 revolutions per second. Calculate the acceleration of the poi ball. The rate of the circular motion is 0.58 meters. The child comments that as the ball goes around the circle with a constant speed, the size of the force on his hand changes. Discuss whether this comment is correct. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that if we draw a diagram as shown, the small angle, or the change in theta, is equal to change in v over v, as shown here. We know from our previous work that we can say that v is equal to is going to be the angular velocity times by the change in time. So therefore, we can work that through, and the change in angle of theta is equal to v change in time over r. So when we work it all through, v, which is equal to the change in time over r, is equal to change in v over v. So therefore we can say quite comprehensively that change in v over t is equal to v squared over r. Next, we know that omega is going to be, so v is equal to 2 pi f, which is omega, times by r. So 2 pi times by 1.3 times by r, which is 0.58, is 4.71 meters per second. A is equal to v squared over r, so we can take that v divided by r and we get 38.7 meters per second squared. Now the centripetal force is the force on the hand. Now the tension acting is constant, but the weight of the ball will be acting towards the centre of the circle at the top, so we would add it. The weight is then subtracted from the tension at the bottom because it's acting away from the centre. So actually the force does vary on the hand and the child is correct. If the Earth orbits in the Sun in a circular path that we know 1 year is 3.2 times 10 to 7 seconds, the radius of the orbit is 1.5 times 10 to 11 meters, and the mass of the Earth is 6 times 10 to 24 kilograms, calculate the angular velocity of the Earth, the linear speed of the Earth, and the centripetal force needed to keep the Earth in orbit around the Sun. So, pause the video now, then unpause the video when you want to go through your answer. In this first one, we know angular velocity is 2 pi f. We know what f is, we can also work it through by saying it's 2 pi over t. So therefore, we can say it's 2 pi over 3.2 times 10 to 7. So it's 2 times 10 to the minus 7 radians per second. V, the linear speed, is r omega. Pop in all the values and we get 29,000 meters per second. Finally, the centripetal force is F equals mv squared over r. Pop in all the values, we've got the mass, we've got the velocity, and we've got the radius. So we get 3.5 times 10 to 22 newtons. A small object of mass 80 grams is attached to a string of length 1.2 meters and is swung in a vertical circle. It travels at a linear speed of 4.8 meters per second. Calculate the tension at the highest point and the tension at the lowest point. So pause the video now, then unpause the video when you want to go through your answer. At the highest point, we can say that the centripetal force, which is mv squared over r, is going to be equal to T minus mg, because mg is acting downwards and tension is acting upwards at that particular point. So therefore, we can say tension is equal to the centripetal force minus mg. So we can say F, which is mv squared over r, pop in all the values, you get 1.536. So therefore T is equal to 1.536 minus 8 times 10 to the minus 3. We're going to turn 80 grams into kilograms. Then times by 9.81, so it's 1.536 minus 0.7848, so it's 0.75 newtons. While tension at the lowest point, we can now say that tension is equal to, tension minus mg equals force, because we know that the weight is acting away against the motion and tension is acting towards, mg is acting away from the centre and tension is acting towards the centre. So therefore the centripetal force, which is mv squared over r, is equal to T minus mg, so T equals F plus mg. F is equal to mv squared over r, pop in all the values, and we get our answer to be 1.536. So therefore we add that to 80 times 10 to the minus 3 times by 9.81. So you add the two values and you get 2.3 newtons. A light aircraft flying horizontally at 70 meters per second has a propeller of radius 0.5 meters, which makes 20 revolutions per second. Calculate the velocity of the tip of the propeller. When the propeller is at its highest point, calculate the force experienced by a 0.2 gram mass attached to the tip, and then state what provides this force. So, pause the video now, then unpause the video when you want to go through your answer. Firstly, calculating the velocity of the tip of the propeller. We know omega is equal to 2 pi f, and we know that the frequency is the revolutions per second, so it's 2 pi times by 20, so it's 40 pi. V is equal to r omega, so therefore we pop this all through and we get 62.83 meters per second. Now, since the plane is moving forwards as the propeller is rotating, the two velocities are at right angles to each other, so therefore can be combined using the Pythagorean theorem to find the resultant velocity. So we've got r squared is equal to the value we just worked out, 62.83 squared, plus the horizontal velocity, because that's 70 squared, so it's 8,847, so r is equal to 94 meters per second. We know F is equal to mv squared over r. We've got our mass, which we know to work through. We've got our velocity, we know 62.83 squared. We divide it by r, 0.5, so we get 1.58 newtons. Now this is the centripetal force, this is the resultant force, and it's provided by the gravitational force here, because what is happening is it's going around at the highest point, so therefore it's being pulled back towards the centre by the gravitational force. So if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and then understand what topics we need to improve upon for A-Level Physics. So thank you for watching this revision session on further mechanics, which is part of AQA A-Level Physics Paper 1 on the concept of circular motion. Thank you so much and have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics on the topic of periodic motion, which is found in paper 1 of the course. So in today's revision session we're going to be looking to answer examination questions on A-Level Physics paper 1, in particular those questions on periodic motion. So if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics examination style questions for periodic motion, assess your understanding on A-Level Physics for periodic motion, and understand what topics of AQA A-Level Physics in the concept of periodic motion you need to improve upon. So how should you prepare for this revision session? When you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. Okay, and then in this section write down your working out and answers to the questions in the revision session. Now when you're doing this, make sure to write these answers in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should we revise for your A-Level Physics? The first step is to learn the key facts. Use the revision guides, the class workbooks, the student prep notes and the textbooks to learn the key ideas of the course, and you might wish to write mind maps and write out notes for yourself. Now the second step is to test yourself, so that's to use things like Caboodle, Seneca, student knowledge checkers, and quickly test your knowledge. You might even want to make your own cue cards to do this. Then the third step finally is to practice exam questions, so use things like exam prep books, homework books, supervised study books, additional workbooks to help answer examination questions and mark your own work. You may even wish to download your own examination past papers to do this. Okay, so the three steps of learn the key facts, then testing yourself, and then practicing exam style questions are how you should be revising A-Level Physics. Now in this revision session we're going to have a look at three different types of questions. The first types of questions are the general check questions. These are the basic questions designed to probe your understanding of the key concepts of the topic. Then we've got our checkpoint question. These are the more challenging questions designed to place your knowledge and understanding of the topics into different contexts. Then finally we've got assessment point questions. These are past paper examination questions which will mimic the types of questions found in public examinations. So let's now start to look at the concept of periodic motion. So State and justify whether the following oscillations show simple harmonic motion. So you've got a basketball being bounced repeatedly on the ground, a guitar string vibrating, a conducting sphere vibrating between two parallel oppositely charged metal plates, and the pendulum of a grandfather clock. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, remember what the definition of simple harmonic motion is, and that's the idea that there's a restoring force which acts always towards the center of the equilibrium or the oscillation, and the size of this restoring force is directly proportional to the displacement is from the center equilibrium position. So the first one is not simple harmonic motion because you've got constant acceleration of the gravity towards the ground, but not when it's hitting the ground or when it's hit by the player, so it's not going to follow those rules. The second one, a guitar string vibrating, yes, that is. There's always a restoring force towards the equilibrium point, and it is proportional to the displacement from that point. The third one isn't simple harmonic motion because it travels with a constant acceleration towards each plate and then suddenly reverses its direction of velocity upon hitting the plates. But the last one is simple harmonic motion because there's a restoring force directed towards the equilibrium point and is proportional to the displacement from that point. The next question says, in each of the examples below, give the phase difference between the two curves shown and then indicate that as a fraction of an oscillation, then have it in degrees and then give it in radians. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we can see that the two oscillations have a difference of half a cycle. Now we know an entire cycle is 360 degrees, so it's 180 degrees, and an entire cycle is 2 pi radians, so this one is pi radians. You'll see in the second one, each of them is out by a quarter of a cycle because you can see that one of the waves is a quarter of a cycle ahead compared to the other wave at that particular point. So they've got a difference of 90 degrees, and they've then got a difference of pi over 2 radians. In the last one, it's a bit more challenging. You'll see that actually the cycles are different by 3/8 of the cycle. So when you do 3/8 times by 360, that's 135 degrees, and do 3/8 times by 2 pi radians, it's 3 pi over 4 radians. The next question says, the figure below shows two oscillations which are out of phase. By what fraction of an oscillation are they out of phase? And why would it not make sense to ask the same question about the third figure in this particular diagram? So pause the video now, then unpause the video when you want to go through your answer. Right, so you can tell that they're out by half an oscillation in that B figure because you can see that that one of the oscillations is a half of a wave cycle ahead of the other one. Now, you can't ask the same thing about the one at the bottom, figure C, because you'll notice that the two waves have different frequencies, so they're not going to be coherent because their phase difference is continually changing, so you can't compare their phase difference. The next question says, the pendulum of a clock is displaced by 4 centimeters and it oscillates in simple harmonic motion with a period of 1 second. Firstly, write down an equation to describe the displacement of the pendulum bob with time, then calculate the maximum velocity of the pendulum bob and then its velocity when its displacement is 2 centimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, this first one, it is an equation which we do cover. So it's actually going to be x is equal, the displacement is equal to the amplitude times by sine of 2 pi t for this value, and then we know that actually the amplitude in this case is 4 centimeters, or 4 times 10 to the minus 2 if you want to work in meters, and then you can work out your answer that way. Now the maximum velocity, we again are given this equation on our equation sheet. It is 2 pi f times by the amplitude a, so we do 2 pi times by 4. We know that the frequency is in fact 1, because there is one oscillation every second, so therefore it's 25.1 centimeters per second. And then its velocity, well, again, we know we can work out the velocity with the equation for the actual value, which is going to be equal to 2 pi times by the square root of the amplitude squared minus the displacement squared. So you pop in all those values and you get 21.8 centimeters per second. The next question says, use the graph shown in this particular diagram to determine the values of the following quantities: amplitude, period, maximum velocity, and maximum acceleration. So you can find the amplitude, okay, by the following. So in the first graph, you can see its displacement against time, so that maximum displacement is going to be the amplitude, so it's 0.02 meters. You can find the period, because the period is the time it takes for one whole wave cycle. You can find it out from any of the three of them, but you can see that it's 0.40 seconds. If we look at the displacement time graph, it starts at, you look at the peak at 0.1, goes to the next peak at 0.5, so therefore it must be 0.40 seconds. You can find the maximum velocity by looking at the max point on the velocity time graph for an oscillator. So you can see it's 0.31 meters per second, and then you can find the maximum acceleration by once again looking at the maximum point on the acceleration time graph. So it's 5 meters per second squared. The next question says, state what point in an oscillation the oscillator has a zero velocity but a positive acceleration, and then look at the displacement time graph below. When the time is 0.1 seconds, what is the gradient of the graph, and state the velocity at this instance. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, when does it have a zero velocity but a positive acceleration? Well, it has a zero velocity at a maximum displacement. So the extreme left, the maximum negative displacement. Now, it has to be the maximum negative displacement because the acceleration has to be acting towards the center. So therefore, it must be a positive and going towards the right. I mean, you could also have it vice versa if you've altered your positives and negatives, but they've got to be in opposite directions. Now, in this one, you'll see at 0.1 seconds, the gradient, okay, you can work it through, is going to be 0 because it's at a maximum point. So therefore, the velocity, which is the gradient of a displacement time graph, that's revision from the mechanics module, is the same value. The next question says, the figure shows the displacement time graph for an oscillating mass. Use the graph to determine the following quantities. The velocity in centimeters per second when time equals 0 seconds, the maximum velocity in centimeters per second, and the acceleration in centimeters per second squared when the time equals 1.0 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see at time equals t equals 0 that the gradient is in fact going to be equal to 0, and the gradient is the velocity of the particular object, so therefore our answer is 0. Now, what's the maximum velocity going to be? You can tell it's actually going to be when you're going through 1 second there, because that's going to be when it's at its highest gradient. So what you can then do, so it therefore is work out the gradient at that point, so it's 47 centimeters per second, and then finally, when t equals 1 second, you can remember the premise of simple harmonic motion is that displacement is directly proportional to the acceleration. So you'll notice here that actually at this point here that we're going to have at the value of t equals time equals 1 second, because the displacement is 0 and the acceleration is directly proportional to the displacement, well, the acceleration will also be 0 as well. The next question says, determine the frequency and the period of the oscillation described by the graph in the figure below. Use a copy of the graph and on the same axis sketch the velocity of the particle and the acceleration of the particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, you've got to remember, how can you work out the frequency and time period? Well, the time period is going to be the time it takes to go from one point on the wave to the next point on the wave, which is the same. So therefore, in this case, the time period is 8 milliseconds. Frequency is 1 over time. You convert your milliseconds to seconds. 1 over 8 times 10 to the minus 3 is 125 hertz. Now, from the graph, how can you work it through? Well, you've got to remember firstly that in your acceleration graph, you've got to remember the acceleration is directly proportional, okay, to the displacement in the opposite direction. So you can see here the blue line represents the acceleration, and it's in the opposite direction to the displacement at all points. Now, the velocity, you'll think about it, is staggered across. So you'll think, remember, there's a phase difference here, because when the displacement is a maximum, the velocity is a minimum, and when the displacement is 0, the acceleration is a maximum. You can plot those points and sketch it through, and you get the red line as shown. The next question says, the figure below shows the displacement of a body as it vibrates between 2 points. State and explain where the body is moving with simple harmonic motion, and then on a second set of axes on your copy, show the velocity of the body as it vibrates. Then on the third set of axes on your copy, show the acceleration of the body. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's not going to be simple harmonic motion because simple harmonic motion shows a displacement with a sine or cosine relationship with time. So you'll notice in this displacement time graph, because it's not that sine or cosine value, you don't have a directly proportional relationship between the actual displacement from equilibrium and the actual acceleration of the object either. Now you'll notice that in the velocity time graph, well, the velocity is going to be the gradient of the displacement. So you can see here that at some points you've got a constant gradient in your displacement time graph. So you have a constant velocity. Then you'll have a zero when you'll have no gradient on the displacement time graph. You've got a zero velocity, so it works through as such. Now the acceleration time graph is therefore again going to be linked to the gradient of the velocity time graph. So you'll see at the start here, you've got no gradient at the velocity time graph, so you've got a zero acceleration. You then got a very steep gradient on your velocity time graph, so you'll get that acceleration. Now you'll note that the acceleration is in the opposite direction to the displacement, as shown on the displacement time graph. So when the displacement is a positive, the acceleration produced will be a negative, and it works through as shown. The next question says, an object moving with simple harmonic motion goes through 2 complete cycles in 1 second. Firstly, calculate the time period, then the frequency, and then the angular frequency. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we know that the time period is the time it takes to go through 1 complete cycle. So therefore, if there's 2 complete cycles in 1 second, well then the time period is going to be 0.5 seconds. Frequency is 1 over time period, so it's 1 over 0.5, which is 2 hertz. Then the angular frequency, much like circular motion, is 2 pi f. So therefore it's 2 pi times by 2, 4 pi radians per second. The next question says, the figure below shows the displacement time graph for an oscillating mass. Use the graph to determine the following: the amplitude, the period, the frequency, the angular frequency, the displacement at A, the velocity at B, and the velocity at C. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, you'll see the amplitude is the maximum displacement, 0.20 meters. The period is the time it takes for the wave to repeat itself, 0.4 seconds. The frequency is 1 over the time period, 2.5 hertz, or 2.5 seconds to the minus 1. Angular frequency is 2 pi f, so therefore it's going to be 2 pi times by 2.5, so 5 pi radians. The displacement at A, you can then work it through off the graph by measuring it. It's minus 0.1, minus being important because it's displacement, so it must have a direction. The velocity at B is going to be the gradient of your displacement time graph, so therefore it's 0 meters per second. And then the velocity again is the gradient at that point, so it's 3.1 meters per second. The next question says, to start a pendulum swinging, you pull it slightly to one side. What kind of energy does this transfer to the mass? And then describe the energy changes that occur when the mass is released. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know it's been pulled to the side, so it's been pulled away from equilibrium, so it's gained gravitational potential energy. Now, when the mass is released, we know for a simple harmonic oscillator, the gravitational potential is then transferred to the kinetic energy. That then reaches a maximum when the ball passes through the equilibrium, the lowest point, because it's at its maximum velocity. Then this kinetic energy is once again converted back to gravitational potential in a cycle. The next question says, the figure below shows how the different forms of the energy change with displacement during simple harmonic motion. Copy the graph and then show how the graph would differ if the oscillating masses were only given half the initial input of the energy. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to be aware it's going to follow the same pattern, but now the total energy is half that, so the horizontal line goes to half the value, but the potential and kinetic still follow the same pattern. But it's important to note that for both instances, the maximum displacement of the oscillator is going to be less, but the relationship is not directly proportional, so it doesn't go to half. The next question says, sketch a graph showing how the kinetic energy and the potential energy of a mass spring system varies with displacement. State any assumptions that you make. Label the amplitude and maximum minimum kinetic and potential energies. Then the total energy of a mechanical oscillator is 1.6 joules. State the maximum values of its kinetic energy and potential energy. The oscillator has a mass of 0.120 kilograms. Calculate its speed when the potential energy of the oscillator is 1 joule. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's the same graph that we had before. So you'll see on here, the total energy remains constant throughout, and the kinetic and potential energies will overall add to the total, but they'll go from maximum to minimum in inverse patterns. So when the kinetic is a maximum, the potential is a minimum, and vice versa. Now this next one, what's the maximum value of kinetic energy and potential energy? Your maximum kinetic energy comes when the potential is 0, so therefore it's 1.6 joules. And whilst the maximum potential energy is when the kinetic energy is 0 joules, so therefore that is also 1.6 joules. Now this next one, you'll see here that we know that the kinetic energy is a half mv squared, but what's the total kinetic energy going to be? Well, the total kinetic energy going to be is the total energy in overall minus the potential energy. So it's 1.6 minus 1, so therefore it's 0.6 joules. So we say 0.6 joules is the kinetic energy, so therefore V equals, it's the square root of 2 ek over m. We've rearranged ek as a half mv squared, so we get 3.2 meters per second. The next question says, a short pendulum oscillates with simple harmonic motion such that its acceleration is related to its displacement by the equation A equals minus 300x. Determine the frequency of the oscillations. Then the pendulum of a grandfather clock swings from one side to the other in 1 second. The amplitude of the oscillation is 12 centimeters. Work out the period of its motion, the frequency, the angular velocity. Then write an equation in the form of A equals minus omega squared x to show how the acceleration of the pendulum weight depends on its displacement. Then calculate the maximum speed of the pendulum bob, and then calculate the speed of the bob when the displacement is 6 centimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we can say is we know for simple harmonic motion A equals minus omega squared x. So we can say minus 300 is equal to minus omega squared x. The x's will cancel through, so we now can say omega, okay, which we can work through here, is 2 pi f. So therefore, when we cancel everything through, we can then say, well, omega is going to be equal, okay, to the square root of this 300 divided by 4 pi squared, so we get to 2.8 hertz. In the next question, we've got to remember that the period is the time it takes for the oscillator to go from one side to the other and back to the original side again. So because it's going to one side, okay, in 1 second, it's got to go back, okay, to double it, so therefore it's 2 seconds. The frequency, therefore, is going to be equal to 1 over time period, 1 over 2, which is 0.5 hertz. The angular velocity is 2 pi f, so therefore it's going to be 3.14 radians per second. Next, we know A equals minus omega squared x, and we know omega is going to be equal to 3.14, so therefore it's going to be minus 3.14 squared times by x, so it's minus 9.87x. The maximum speed, well, we know from the equation sheet that Vmax is equal to, okay, the idea of omega, 2 pi f, times by the amplitude, which is x0 in this particular notation. So therefore it's 3.14 radians per second times by the maximum, which is 12 centimeters. So we work it in centimeters here, so therefore the speed is 38 centimeters per second. Then the speed, we know the equation is going to be equal to V equals omega times by the square root of amplitude squared minus x squared. Pop in all the values and we get 33 centimeters per second. The next question says, give one example of a free and a forced oscillation. Describe how dampening affects the amplitude of an oscillating object. Then sketch the graph of a displacement against time for a simple pendulum with firstly no dampen and then secondly with a small amount of dampen. So pause the video now, then unpause the video when you want to go through your answer. Right, so a forced oscillator is when you've got something driving the oscillation. So it could be a mass spring system attached to a vibration generator, Barton's pendulums, a person on a swing, whilst the free oscillation is something that just oscillates without a driving factor. So it could be a mass spring system, a pendulum, a ruler oscillating over a desk. Now dampening is important because dampening will reduce the amplitude over time because energy is dissipated out of the system and amplitude is an expression of the energy in the system. Now if there was no dampening, we'd see a sinusoidal pattern, so a sine curve with a constant time period and a constant amplitude. Now if you've got a small amount of dampening or light dampening, whilst the amplitude will decrease exponentially for your sine graph, the actual time period remains constant throughout. The next question says, when a cricket bat So when a cricket ball hits a cricket bat at high speed, it can cause a standing wave to form on the bat. In one such example, the handle of the bat moved with a frequency of 60 Hz and an amplitude of 2.8 mm. The vibrational movement of the bat handle can be modelled as simple harmonic motion. State the conditions for simple harmonic motion. Calculate the maximum acceleration of the bat handle. Given that part of the bat handle held by the cricketer has a mass of 0.48 kilograms, calculate the maximum force produced on his hands. Then the oscillations are damped and die away after about 5 complete cycles. Sketch a displacement time graph to show the oscillations. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's the definition? You've got to learn these. It's the idea that there is always an acceleration towards an equilibrium position in simple harmonic motion, and that the magnitude of the acceleration is proportional to the displacement from the equilibrium position. Now we know in simple harmonic motion, acceleration is equal to omega squared A, or in this case omega squared r. Now again, you've got to remember that the amplitude has to turn into 2.8 millimeters into meters, and omega is 2 pi f, so it's 2 pi times by 60. So when you work it through, you get 400 meters per second squared. Now we know F is equal to ma because in periodic motion it still follows Newton's laws, so therefore F equals ma. You've just worked out A in the previous question, you know M from the information given, so it's going to therefore be 400 times by 0.48, which is 190 newtons. Now in this next one again, like we said, the time period remains constant throughout the oscillations, but the amplitude decreases exponentially, so it should follow the following pattern. Next question, sketch the graph to show how each of the following quantities changes during the course of a single complete oscillation of an undamped pendulum. Kinetic energy, potential energy, total energy, then state how your graphs will be different for a lightly damped pendulum. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to think about what's actually going on. So the total energy remains unchanged throughout the actual oscillation. But when the potential energy increases, the kinetic energy decreases and vice versa, and they vary on that complete cycle as shown there. But that's an undamped pendulum. Now, if it was a lightly damped pendulum, the total energy of the pendulum would decrease over time. So therefore, the maximum values of kinetic energy and potential, because they're going from one to the other, but also being lost at the same time, would also decrease. The next question says, list 3 examples of situations where resonance is a problem and 3 other ones where resonance is useful. In each case, state what the oscillating system is and what forces it to resonate. So pause the video now, then unpause the video when you want to go through your answer. Right, so problems could be buildings and earthquakes. So the mechanical structure is forced to oscillate from energy from the waves of the earthquake, which could cause them to collapse. You've got components in engines, so at certain rates of rotation, parts of the engine may resonate mechanically, with this resonance being driven by the energy output of the engine. So this can lead to the components in the engine cracking or disintegrating, and then the engine can fail. The next one is positive feedback in amp systems. So if a microphone is held too close to a loudspeaker, which is emitting waves of the same frequency that the microphone is tuned into, i.e. the actual sound wave that's being put out of the speaker, well then the sound waves from the loudspeaker will force the amplifier to resonate and produce that positive feedback. 3 useful parts of resonance would be a tuned radio. So the electrical signal in a circuit is forced to oscillate by the incoming radio waves and resonate, and that allows you to hear the radio signal. You've got a microwave cooker where the water molecules are forced to resonate by the microwave with heat of the food. And you've also got magnetic resonance in atoms where the nuclei and atoms behave as magnets. They can be made to resonate by electromagnetic waves. Now each nucleus resonates at a different frequency because they've got a different number of components in their atoms, so therefore we can work out the structure of the molecules in MRIs. Next question says, sketch a graph of amplitude against the driver frequency for an experiment on a mass spring forced oscillation. Use the graph to explain the effect of resonance on an object. Explain why a glass shatters when exposed to a sound at the natural frequency of the glass. Then the side panel of a tumble dryer vibrates loudly when the dryer spins at a specific angular frequency. Explain why it only happens at a certain frequency and suggest a technique to reduce the vibration. So pause the video now, then unpause the video when you want to go through your answer. Right, so you should be able to remember the graph of the amplitude against the driving frequency. The amplitude will increase as the driving frequency goes to hit the natural frequency. The amplitudes of the oscillations are maximum when the natural frequency equals the driving frequency, that is resonance, and then once the driving frequency goes above the natural frequency of the system, the amplitude will decrease. So glass will shatter because glass will resonate, okay, at the frequency when the driving frequency of the sound is equal to the natural frequency of the glass. That will increase the amplitude of oscillations because resonance is occurring. That amplitude becomes so large that the glass will break from it because it doesn't have the mechanical structure and support to hold it together. Now, the next question, when you've got a spinning drum in a tumble dryer, that creates a driving force on the panel. Now, the driving force on the panel is related to the angular frequency of the drum spinning in the dryer. So when the driver frequency is equal to the natural frequency of the panel will then resonate, so that to reduce the amplitude of the panel, you can install dampener, because dampener will dissipate energy out of the system, so you can install rubber or foam pads to it. The next question shows the piston of a small car engine which oscillates in the cylinder with a motion which approximates simple harmonic motion at 4,200 revs per minute. Okay, the mass of the piston is 0.24 kilograms. Explain what's meant by simple harmonic motion. Calculate the frequency of the oscillation. The amplitude of the oscillation is 12.5 centimeters. So calculate the maximum speed at which the piston moves, the maximum acceleration of the piston, and the force required on the piston to produce maximum acceleration. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's simple harmonic motion? Once again, it's that there's always acceleration towards an equilibrium position, and the magnitude of this acceleration is proportional to the displacement from this equilibrium position. The frequency, well, we know that there are 4,200 revolutions per minute. The frequency is the revolutions per second. It's 4,200 divided by 60, which is 70 hertz. Now we know that maximum speed is equal to r omega, so therefore we can do the value for omega, which is 2 pi f, so it's going to be 2 pi times by 70, times by r, which we can tell is going to be 12.5 centimeters, so therefore it's 12.5 times 10 to the minus 2 meters, so we multiply the two together to get 55 meters per second. We know acceleration from the equations is equal to a equals minus omega squared a, or minus omega squared r, because the amplitude is the radius in this example. So we can pop it through and get that to be 24,000 meters per second squared. We know that from if it obeys Newton's law, so F equals ma. So you've got your value of A is 24,000. You know the mass in the question is 0.24. Multiply them together, we get 5,800 newtons. The next question says, doctors can use ultrasound to monitor the heartbeat of a baby when it's developing inside the mother. A baby's heart was beating at 142 beats per minute. The wall of the baby's heart was moving at a maximum velocity of 22 millimeters per second. Calculate the maximum displacement in millimeters of the wall of the baby's heart. Assume that the motion of the wall of the baby's heart is simple harmonic. The motion of the wall of the baby's heart only approximates the simple harmonic. State what is meant by simple harmonic motion. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can work out what the frequency is. So the frequency is 142 beats per minute, so it's how many beats there are per second. So you divide it by 60, so it's 2.37 hertz. Omega equals 2 pi f, so it's at 14.9 radians per second. We then can look at our equation sheet and see that the maximum displacement is linked to the idea of the amplitude, and we know that Vmax is equal, therefore, okay, to omega times by a, because sine omega t is equal to 1. So therefore a is going to be equal to the maximum velocity, which you know is 22 times 10 to the minus 3, because we go over millimeters to meters. We divide it by 14.9, which is going to be, when you're working through there, linking into the idea of the angular velocity. So therefore it's 1.48 times 10 to the minus 3 meters, which is 1.48 millimeters. Again, learn the definition of simple harmonic motion. It is the idea that there's always a resultant force proportional to the displacement of equilibrium position, and the force is always acting towards that equilibrium position. The next question says, a can of spray paint needs to be shaken before being used. The diagram shows a machine designed to shake a can of spray paint. The bracket oscillates vertically with simple harmonic motion. State the conditions necessary for an object to move with simple harmonic motion. When the bracket is oscillating, the distance between the highest and lowest positions of the bracket is 8 centimeters. The bracket completes 270 oscillations per minute. Sketch a graph to show how the velocity of the bracket depends on the time. You should include velocity and time values on your graph. then determine the maximum acceleration of the bracket, then suggest why the particles of paint in the can will experience a maximum acceleration that's different to the previous answer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, like we said before, learn the concept of simple harmonic motion and its criteria. So there's a resultant force that's proportional to the displacement from equilibrium, and that force is always acting towards the equilibrium position. In this next one, we can say F is equal to 270 divided by 60, so it's 4.5 Hertz. Omega equals 2 pi F, so it's 28.3 radians per second. And V equals omega R, so it's 1.13 meters per second. And then you can use that to then draw your graph of the values for V and T on the axis, because you've just worked out the maximum velocity that you would require. Next, what's the maximum acceleration? Well, we know A equals minus omega squared A, or minus omega squared R for working on maximum acceleration. You've got omega from the previous question. You know R, it's going to be 4 times 10 to the minus 2 meters, so it's 32 meters per second squared. Now, why will they experience different maximum acceleration? Because the particles themselves are free to move inside the can. So not all the particles will actually move with simple harmonic motion, and because that means the amplitude of the oscillation of the particles will be different to the amplitude of the can. The particles might continue to move upwards as the can starts to move downwards, and then the particles collide with each other, and the force on the paint particles is not equal to the force on the can, so therefore you'll get all different values. The next question says the figure below shows how the velocity of a 2 kilogram mass was found to vary with time during an investigation of simple harmonic motion of a pendulum. Use the graph below to estimate the following for the mass: its maximum velocity, its maximum kinetic energy, its maximum potential energy, its maximum acceleration, and the maximum restoring force acting upon it. So pause the video now, then unpause the video when you want to go through your answer. Right. So in this one, the maximum velocity is the peak of the graph, which is 0.35 meters per second. The maximum kinetic energy is therefore going to be a half mv squared with the adjusted value of v for the maximum velocity. So you work it through and you get 0.12 joules. The maximum potential energy will equal the maximum kinetic energy because that is the maximum energy of the system. So it's going to be 0.12 joules. So therefore, what's the maximum acceleration? Well, we know maximum acceleration. We know it can work through, okay, from the information given, because we know it's going to be minus omega squared A. We know we can work those through, so therefore we get 0.17 meters per second squared. We know F equals ma, so it's 3.4 newtons. The next question says, show the graph of displacement against time for an oscillator. Okay, sketch the graph to show the variation of potential energy with time and the kinetic energy with time. Then a simple pendulum has a mass of 50 grams. It is initially released from an amplitude of 0.050 centimeters and has a frequency of 0.40 hertz. Calculates kinetic energy 2.8 seconds after release. Then show that the maximum kinetic energy of an object moving in simple harmonic motion is given by the equation maximum kinetic energy is equal to 2m pi squared f squared a. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would it look? So you've got to see that when you have when you've displaced it from equilibrium to start off the oscillation, you'll get a maximum potential. It'll then drop to zero when it's going through equilibrium because it's got no displacement from equilibrium, and it works through like that. Remember again, potential can't be a negative, it's a scalar, so therefore you would never get a graph below the x-axis. Now kinetic energy opposes that one, so it's the opposite one, because when you've got a maximum potential, you've got a minimum kinetic and vice versa. Now next one, you can say omega equals 2 pi f, so therefore it equals 2.5 radians per second. From the equation sheet, x equals a cos omega t, so you pop all those values through to get 0.038 meters. We then can again look on the equation sheet to work out the velocity equation, and you can pop it in to get plus or minus 0.081 meters per second. Therefore the kinetic energy is going to be half mv squared from those previous values, 170 times 10 to the minus 6 joules. Now we know that kinetic energy is equal to half mv squared, so maximum is when we go to Vmax. We know also from simple harmonic motion on the equation sheet, Vmax equals omega A, omega is 2 pi f, so therefore Vmax squared is therefore going to equal to 4 pi squared f squared times by a squared when we sub in the values. Pop that into the equation half mv squared, so therefore we get 2m pi squared f squared a squared. The next question says, a trolley of mass m is fixed to the end of a spring. The spring can be compressed and extended. The spring has a force constant, k. The other end of a spring is attached to a vertical wall. The trolley lies on a smooth horizontal table. The trolley oscillates when it's displaced from its equilibrium position. Firstly, show that the motion of the oscillating trolley is simple harmonic motion, and then show that the period for the trolley is given by the equation t equals 2 pi square root m over k. So, in this one, you've got to prove that A is directly proportional to F, and therefore A is directly proportional to X. So, therefore, we know that the force acts in the opposite direction to the displacement, so therefore it must be simple harmonic motion. Now we know from Newton's second law, A equals minus F over m. It's a minus because we know that the force is always acting towards the equilibrium, so the opposite direction to the displacement. So now we know in the spring constant, F equals kx, so we can sub that in. And we also know that because it is simple harmonic motion, A equals minus omega squared x, where x is going to be the displacement. So therefore we can cancel everything through. We can say omega squared equals k over m, so omega equals square root k over m. We know that omega equals 2 pi f, so f equals omega over 2 pi. Pop in all the values, work it through, t is 1 over f, so we get 2 pi times by the square root of m over k. The next question says, if the amplitude of a mass oscillating freely at the end of a spring is doubled, what happens to the time period of the oscillation? Then a horizontal spring has one end fixed to a wall and a trolley attached to the other. The trolley is pushed to the right by 4.9 centimeters with a force of 2.8 newtons and then released. It oscillates with a simple harmonic motion with a time period of 0.44 seconds. Calculate the mass of the trolley. Then what would a graph of t squared against k look like for a mass oscillating a spring? So pause the video now, then unpause the video and you'll want to go through your answer. Right, so you'll notice that the time period of a mass oscillating does not depend on the amplitude of oscillation. So t does not have a value of a in this equation, so therefore the amplitude would not change the time period. Now we know that we're given here the force, okay, and we've got our extension or our change, so therefore we can say k is equal to F over delta L. Remember, we turn centimeters into meters, so we get k to be 57.1 newtons per meter. We know that for this case of a mass spring system, t equals 2 pi times by the square root of m over k, so therefore you can rearrange it, make m the subject, pop in all the values, and you get 0.28 kilograms. Now, how would this graph look like? Well, we know t squared is directly proportional to 1 over k because we know that 2 pi and m will be constant in that particular equation. So the graph will be an inversely proportional relationship, and there'll be a line of best fit with a negative gradient becoming less steep, because that's what an inverse proportion graph looks like. The next question says, Skylab was an early space station that orbited the Earth. Skylab contained a body mass measurement device. The device was a chair connected to a stiff spring. Astronauts in orbit around the Earth are sometimes described as weightless, although they do experience a weight force. Explain why astronauts may be described as weightless. Then the spring was tested without oscillating. A force of 175 newtons was applied to the spring, and the spring deformed by 28.9 centimeters. When no one was sitting in the chair oscillated with a period of 0.858 seconds. When one of the astronauts sat in the chair oscillated with a period of 2.26 seconds. Calculate the mass of the astronaut. So pause the video now, then unpause the video and you'll want to go through your answer. Right, so this one, the idea is the astronauts are moving in a circular orbit, so they'll experience a centripetal force as they orbit. Now, the weight of the astronaut is acting as the centripetal force, is acting towards the centre of the circular orbit. So therefore, the astronauts are free falling, they are accelerating towards the centre of the Earth, okay, as they orbit it, but they'll have inertia in the vertical direction, so therefore they'll be moving in a circle and they'll be free falling and they'll not be touching any object, they'll not be touching the bottom of the spaceship, so they won't experience a contact force which we would observe as weight on Earth. In the next question, once again, we can work out k by doing k as F over delta L. Remember, we're going to be in meters, so convert our centimeters into meters there. So we get 606 newtons per meter. T equals 2 pi over the square root of m over k. So therefore, you can work out the mass by doing the mass when it is not got when it has an astronaut in the chair and a astronaut without the chair. So the mass will be by the astronaut with itself, 11.3 kilograms. Then we've got the mass of the astronaut and the chair, 78.3 kilograms. So the difference between the two is the mass of the astronaut, 67.0 kilograms. The next question says, a simple pendulum has a period of 2 seconds on the Earth. Calculate what the period would be if the pendulum was on Venus, with the mass of Venus being 4.87 times 10 to the 24 kilograms, and the radius of Venus being 6.05 times 10 to the 6 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you can say is we know from the gravitational fields module G equals gm over r squared. So from the information given for Venus, we can work out the acceleration due to gravity on Venus. So it's 8.87 newtons per kilogram. Now we can say that if t equals 2 pi over the square root of L over g, that t is directly proportional to 1 over g square root of 1 over g. So therefore we can actually ratio this and say t Venus over t Earth is equal to the square root of g Earth over g Venus. So you can pop it all through and you do the square root of 9.81 over 8.87, which is 1.05. So it's telling us the time period on Venus will be 1.05 times greater than the time period on Earth. Time period on Earth is 2 seconds, so on Venus it would be 2.10 seconds. The next question says, a simple pendulum can be used to determine a value for g. When the pendulum is displaced through a small angle theta and released, it performs simple harmonic motion about its rest position. The student uses this 85 centimeter pendulum to determine a value for g. He times 3 complete oscillations and obtains a time of 5.61 seconds. Calculate the value of g given in this data, and then express your answer to the appropriate number of significant figures. Suggest and explain one way in which the student could refine the experiment to get a more precise value for g. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we can say is we know that the time period is going to be 5.61 divided by 3, because there's 5.61 seconds for 3 oscillations, so it's 1.87 seconds. We know L is going to be 85 centimeters in meters, 0.85 meters. We know T equals the square 2 pi times the square root of L over G. Rearrange, make G the subject, pop by the numbers, and we get 9.6 meters per second squared. Now, how could you get a more accurate value for G? Well, you could time our oscillations because the percentage error in the timing will be reduced by dividing by when you do your number of oscillations. You could repeat it several times and average it out to reduce random errors. You could repeat it for different values of L and plot a graph of T squared against L to find G, because that will counteract random error produced in the experiment. The next question says, a diagram shows a metronome which includes an inverted pendulum used by musicians to set a tempo. The pendulum oscillates with simple harmonic motion and makes a loud click at regular intervals. A faulty metronome stops making a clicking noise. A student tried to check the accuracy of the period of the metronome using a stopwatch. The student timed the pendulum as it moved from one extreme end of the oscillation to the other. Explain how the procedure used by the student to determine T could have been improved. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to understand that time and a number of complete oscillations and dividing by this time will actually reduce your percentage uncertainty because it increases the time recorded and therefore reduces the effect of the reaction time. You should always time for the midpoint of the oscillation because that's when it's moving the fastest, so it's easiest to identify. You can also use a fiducial marker to identify the midpoint of the oscillation, which is when the pendulum is travelling the fastest, and that will therefore overall make it easier to measure, reducing your percentage uncertainty. The next question says, a data logger is used to monitor the oscillations of a lightly damped oscillator. The results are shown. State Y amplitude decreases with time. State one quantity that remains constant for oscillations and determine the natural frequency of an oscillator. The amplitude of a damped oscillator decreases exponentially with time. At t equals 0, the amplitude is 5 centimeters. The amplitude decreases 90% after each period. The period of its oscillation is 1.0 seconds. Sketch your displacement time graph for this damped oscillator up to the time of 5.0 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, amplitude will decrease with time because dampening will dissipate energy out of the system and towards the surroundings, decreasing the amplitude. What stays constant when you have dampening? It's the time period. Now, if you look on the graph, the time period is 1 second, frequency is 1 over time period, so it's 1 over 2.0, which is 0.50 hertz. Now, when you do your displacement time graph, you'll realise that when you think of where the displacement is compared to equilibrium and how it links into the oscillation, it's going to be a cosine graph. you're going to have a time period of 1 second, which will remain constant throughout. And it'll start off with an amplitude of 5 centimeters. As the amplitude decreases to 90% of the previous value for each cycle. So the first cycle is 5 centimeters. The next one is 90% of 5 centimeters, 4.5. 90% of that is 4.1. 90% of that is 3.6. And 90% of that is 3.3, given your particular cycle. The next question says, in some examples of dampening, the amplitude of a damped oscillating system decreases exponentially with respect to time. Determine the initial amplitude, period and angular frequency of the system below, and use the graph to determine if the amplitude decays exponentially. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the initial amplitude is the displacement at the start, which is 0.25 meters. The time period is the time it takes to go from peak to peak, which you'll see is going to be 4 seconds. The angular frequency is 2 pi over t, so it's 2 pi over 4, so it's 1.6 radians per second. Now, to see if it decays exponentially, what you're going to do is take a fixed time period, like 2 seconds, and see if the values, each point is going to be the same. So at 0, it's the displacement is 0.25. At 2, it's 0.21. So you do 0.21 over 0.25 is 0.84. Then do the same from 2 to 4. You get 0.86. Then do the same from 4 to 6. That's going 0.89. The values are therefore similar. So the value of change is constant, which indicates exponential decay. The next question says, seismometers are used to detect and measure the shock waves which travel through the earth due to earthquakes. The figure shows the structure of a simple seismometer. The shock wave will cause the mass to vibrate and cause a trace to be drawn on the paper scroll. The frequency of the typical shock is between 30 and 40 Hz. Explain why the natural frequency of a spring mass system in the seismometer should be very much less than the range of frequencies. The graph shows the acceleration of mass against its displacement when the seismometer is recording an earthquake. What evidence does the graph give that the motion is simple harmonic motion? And use the information from the graph to determine to calculate the frequency of oscillation. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, when do you get this idea of resonance? So when the driving frequency equals the natural frequency, resonance will occur. That'll give you a massive jump in amplitude, so therefore that'll give a false reading for the shock wave strength because it won't be an accurate reflection of it. The graph below shows simple harmonic motion because it was a straight line through the origin, indicating acceleration was directly proportional to displacement, and because the gradient was a negative, it was in the opposite direction to the displacement. Now, how could you work out the frequency of the oscillation? Well, we know that omega can link in by saying, we know A is going to be equal, to omega squared over r. So therefore, omega squared equals A times r. So therefore, you pop in the values, you work out omega to be 22.3. F equals omega over 2 pi, so it's going to equal 3.6 Hertz. The next question says, a teacher is teaching her class about the phenomena of resonance. To do this, she uses a drinking glass to produce sound waves in 2 different ways. When the glass is gently struck, the glass emits sound for a short time. When a wet finger is slid around the top of the glass, it is possible to produce a loud continuous sound. Explain these observations. So pause the video now, then unpause the video when you want to go through your answer. Right, so striking the glass will set the glass into a free oscillation. Energy is then transferred from the glass and the amplitude of the oscillation will decrease, and then it becomes damped, so because it's damped because the energy is going to the surroundings. Now if you slide a wet finger around the top of the glass, we've now got a forced oscillation because we've got a driving force driving that oscillation. Now the driving frequency produced by the wet finger is then equal to the natural frequency of the glass. That will then cause resonance, which will allow a maximum transfer of energy into the glass. That will increase the amplitude tremendously and you get the resonance effect. The next question says, an object is suspended from a spring. When displaced, the object executes 180 complete oscillations in a time of 1 minute. The upper end of the spring is then suspended from a mechanical oscillator. The spring mass system is forced to oscillate. The frequency of the mechanical oscillator is gradually increased from 0. Sketch a graph to show the variation of amplitude with the frequency of the mechanical oscillator. Then an old van with an undamped suspension system drives over 3 spade bumps 10 meters apart at a speed of 2.5 meters per second. The front end of the van begins to resonate. State the natural frequency of the suspension and explain why driving over the bumps at different speeds will reduce the amplitude of the oscillations. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can work out what the natural frequency is, because it's 180 divided by 60, because it says it's 180 complete oscillations in 1 minute, so therefore it's 3 hertz. So it must be the peak of the graph at that value, because that's when you get your highest amplitude. So as the driver approaches the natural frequency, the amplitude will increase. It reaches the maximum of the natural frequency, that's resonance. Beyond the natural frequency, you'll have your amplitude then drop again, so it'll go back in that curve shape. In this next question, what's the time period between the bumps? Well, they're 10 meters apart, okay? So we can say the time between the bumps is going to be 10 over 2.5, so it's 4 seconds. The time between the bumps is the period of the oscillation, which is 1 over the natural frequency, because it's going to be when it equals the driving frequency. So it's going to be 1 over 4, so it's 0.25 hertz. So that would be the natural frequency, and the driving frequency, which would cause the resonant frequency. Now at different speeds, the time between the bumps would be different, so therefore the driving frequency would change. It wouldn't equal the natural frequency, so you wouldn't get resonance. The amplitude will be lower. The next question says, a body is moving with simple harmonic motion. State 2 conditions that must be satisfied concerning the acceleration of the body. A mass is suspended from a vertical spring and the system is allowed to come to rest. When the mass is now pulled down a distance of 76 millimeters and released, the time taken for 25 oscillations is 23 seconds. Calculate the frequency of oscillations. Calculate the maximum acceleration of mass, and calculate the displacement of the mass from its rest position 0.60 seconds after being released. State the direction of the displacement. So pause the video now, then unpause the video when you want to go through your answer. Right, we've talked about this before. 2 conditions. Acceleration proportional to displacement. Acceleration is in the opposite direction to the displacement or towards the equilibrium position. Frequency is how many oscillations per second, so it's 25 over 23, 1.1 hertz. Acceleration is equal to omega squared a, or 2 pi f squared times by a. Pop in all the values. Remember, 76 millimeters turns into meters, so it's 3.6 meters per second squared. Displacement from the equation sheet is a cos omega t, or 2 pi ft. Pop in all the values. Remember, millimeters turns to meters. Pop in the values, and it's 4.3 times 10 to the minus 2 meters towards the equilibrium position. The next question says, a 150 gram mass was hung from a spring as shown. The spring extended by 7.5 centimeters. The mass was displaced vertically 3.0 centimeters from its equilibrium position and then released. The mass oscillated vertically. Explain why the motion of the mass was simple harmonic motion. Calculate the maximum velocity of the oscillating mass, and explain why the maximum velocity of the oscillating mass decreased over time. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's the 2 conditions? The resultant force is always proportional to the displacement of equilibrium, and it always acts towards equilibrium. Now in this next question, think of all the information you've got. You can say F equals mg. So it's 0.150, because we're using grams into kilograms, times by 9.81 is 1.47 newtons. We know the spring constant is F over x, so therefore it's going to be 19.6 newtons per meter. Remember, it gives you centimeters in the question, converted into meters. We know because it's a mass spring system, T equals 2 pi times by the square root of m over k. Pop in all the values, you get 0.49 seconds. Omega equals 2 pi over t, so it's going to be 2 pi over that value to be 11.4 radians per second. And then finally, Vmax is omega a, because sine omega t trends to 1, so therefore it's 11.4 times by 3 times 10 to the minus 2, the amplitude in meters, and then we go 0.343 meters per second. Now the maximum velocity will decrease over time because you've got dampening forces there. They'll dissipate energy to the surroundings from the system, and dampening is when you go work against those resistive forces. The next question says, here is a young girl swinging on a garden swing. You may assume that the swing behaves as a simple pendulum. Ignore the mass of the chain supporting the seat throughout the question and assume the effect of air resistance is negligible. 15 complete swings took 42 seconds. Calculate the distance from the top of the chains to the centre of mass of the girl in the seat. Express your answer to the appropriate number of significant figures. To set her swinging, the girl in the seat would displace from equilibrium and release from rest. Their initial displacement of the girl raised the centre of mass of the girl in seat 250 millimeters above its lowest position. If the mass of the girl was 18 kilograms, what was her kinetic energy as she first passed through this lowest point? And then calculate the maximum speed of this girl during the first oscillation. So pause the video now, then unpause the video when you want to go through your answer. Right, so this first one, we can say the time period is 42 divided by 15, so it's 2.8 seconds. We know t, because it's a pendulum, is 2 pi over square root L over g. We can rearrange it, make L the subject. We then pop in the values and we get 1.9 meters, and again it's 2 sig figs because you're given two significant figures, 42 and 15, in the question. We know here E equals mgh, and therefore in this case the maximum potential will equal the maximum kinetic, so we'll work through that way. So it's 18 times by 9.81 equals 0.25 equals 44 joules. We know that's the maximum kinetic energy, and equals a half mv squared, so v equals the square root of 2ek over m. We pop in all the values and we get 2.2 meters per second. The next question says, a grandfather clock uses a simple pendulum to keep an accurate track of time. The second hand of the clock moves forward exactly 1 second each time the pendulum moves from A to C, and another second each time it moves from C to A. Determine the length of the pendulum in the grandfather clock that would accurately tell the time. The pendulum is lightly damped. As a result, the clock needs to be wound up once a week. Suggest one possible cause of light dampening in the pendulum. Explain why dampening does not affect the clock's ability to tell time. Then a grandfather clock has a pendulum of length determined in the first part. It is used to tell the time of the Earth's equator, where g equals 9.78 meters per second squared. The clock was set exactly at the right time at 1800 hours on Monday evening. Determine the time displayed by the clock at 1800 hours the following Monday. So pause the video, then unpause the video and you want to go through your answer. Right, in this first one, we do t equals 2 pi times by the square root L over g. We rearrange it. We make L the subject. We pop in all the values. Now again, remember t is 2 because it's going 1 second to one end and 1 second back again, so t is equal to 2. Pop in all the numbers and we get 0.994 meters. Now, because it's lightly damped, what's causing work to be dissipated, against the motion, and it's causing energy to be dissipated to the surroundings? Well, it could be friction at the pendulum pivot. It could be internal friction due to tension in the string, or it could be air resistance. It won't affect the ability to tell the time because the time period does not have an amplitude term in this equation, so therefore reducing the amplitude due to dampening would not cause the time period to change. And in this last one, we can say t equals 2 pi times by the square root of L over g. We know L to be 0.994 meters. We know g to be 9.78 because it's at the equator. So we work it out to be 2.00306. So that tells us that for each time, when the time period is 2 seconds, normally at our position on Earth, it's going to be 2.00306. So therefore we can run it back to 1 second by half in each value. We know in 1 week, the time from 4 p.m. on Monday 1 week to 4 p.m. on Monday the next week is going to be 604,800 seconds. So in that time, the other clock is going to move forward a bit less by dividing by 1.00153 because it's going to move that for every 1 second on the other clock. So there's 925 seconds slower than the recording time, which is 15 minutes and 25 seconds. So actually it'll be slower. So therefore over the week you would lose that 15 minutes and 25 seconds. So it'd actually say on the clock 17:44 and 35 seconds, which is why you need to always calibrate your clocks. The next question shows, during the final stage of a wash cycle, an undamped washing machine increases the rotational frequency of the rotating drum from 0 to 1,250 revolutions per minute. The rotating drum has a diameter of 35 centimeters. Calculate the maximum linear speed that the clothes in the washing machine could reach during the final stage of the washing cycle. Between the rotational frequencies of 600 and 900 RPM, the washing machine can be observed to vibrate. The amplitude reaches a peak at 750 RPM. Explain the shape of the graph shown. Newer models of the washing machine are heavily damped. Describe what you expect the amplitude profile to look like in newer models compared to the graph shown, and then dampening is incorporated into the design of many everyday objects. A set of supermarket scales is damped to reduce the variation in weight measurements when food is put on the scales. State and explain the degree of dampening that's most suitable for this set of supermarket weighing scales. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that you get your Vmax at 1,250 revolutions per minute. Now we know frequency is going to be equal to 1,250 divided by 60, so it's 20.8 Hertz. omega equals 2 pi f, so it's 2 pi times by 20.8, because that's the frequency, so it's 130 radians per second. The radius is the diameter by 2, so it's 35 centimeters or 0.35 meters, divided by 2, so it's 0.175 meters. V max is equal to omega times by r, pop in the numbers, we get 23 meters per second. Now, what's happening? Well, the rotation of the drum forces the washing machine to vibrate at the same frequency. This driving frequency approaches the resonant frequency of the machine, which is the natural frequency of the object, and the machine will resonate and gain more energy from the driving force, so causing it to have a violent increase in amplitude of oscillation. Now, what would happen if you have dampening? Well, the first thing is the profile is flatter, so it's got a wider peak. It's not as sharp, so therefore it'll be a duller peak, but also be a lower peak, and also be slightly less as well compared to an undamped model, so the peak will shift to the left slightly. Now, the type of dampening you want here is critical dampening, because what you want is you want your scale to go straight back to equilibrium as soon as possible. That is critical dampening, so therefore it will reduce the variation because the scales will go back to equilibrium as soon as possible, so therefore you need your critical dampening. That brings an end to our revision session today. So hopefully if you found this revision session useful, you can answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and understand what topics you need to improve upon for A-Level Physics in periodic motion. So thank you so much for attending this revision session on periodic motion. I hope you found it extremely useful, and as always, have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics Paper 1 on the topic of circular motion. So if we're successful and we learn in today's revision session, we should be able to answer examination questions on A-Level Physics Paper 1 on the topics of circular motion. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions for circular motion, assess our understanding on circular motion for A-Level Physics, and understand what topics we need to improve upon for AQA A-Level Physics in the circular motion topic. So how should you prepare for this revision session? Well, when you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the question in the revision session. When you're doing this, make sure to write in full sentences and show the full working out. Whilst on the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for A-Level Physics? So the first step is to learn the key facts. Use revision guides, class workbooks, student prep notes, the textbooks to learn the key ideas of the course. You may wish to make mind maps or write out the notes yourself. The second step is retrieval, testing yourself, using the Caboodle e-learning platform, using the Seneca e-learning platform, using student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. And then finally, practice examination style questions. Use exam prep books, homework books, supervised study books, additional workbooks to answer questions and mark your own work, and you may wish to download your own examination past papers to do this. So you should have the three steps of learn the key facts, testing yourself, and practicing exam style questions. So in this revision session, you'll see three types of question. Firstly, there'll be general check questions, basic questions designed to probe your understanding of the key concepts of the topic. You've got the checkpoint questions, which are the more challenging questions designed to place your knowledge and understand the topics into different contexts and application. And then finally, you've got assessment points, the past paper exam questions which mimic the type of questions found in public examinations. So let's now have a look at the topic of circular motion. The first question says, explain what is meant by a radian. And the second question says, a body moves around in a circle at a constant speed and completes one revolution in 15 seconds. Calculate the angular velocity of the body. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's all about you've got to understand the definition of what the radian is. So by definition, the radian is the angle subtended at the centre of a circle by an arc equal to the length of the radius of the circle. Now the second question, again, is a test of how you work at angular velocity. Angular velocity is 2 pi over t, because 2 pi is the completed displacement in one revolution and t is the time of one revolution. So 2 pi over 15 is 0.42 radians per second, because remember, it's going to be an angular displacement of 2 pi radians in one whole circle. Next question. Express the following angles in radians: 180 degrees, 45 degrees. Then calculate the angular velocity of a roundabout which completes one revolution in 30 seconds, and then a spinning top with a time period of 0.10 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this you've got to be aware of how you can convert angles from degrees into radians, and you could either do it one of two ways. You could remember that there are 2 pi radians in 360 degrees, or you could do the angle in degrees divided by 180 over pi, so therefore it would work to be pi radians, which is 3.14 radians. Again, 45 degrees by those logics will equal a quarter pi radians, or 0.79 radians. Again, angular velocity is going to be 2 pi over t. Now again, it tells you that the time for one revolution is 30 seconds, so it's going to be 2 pi over 30, 0.21 radians per second. And this next one, 2 pi over 0.10 seconds, 63 radians per second. The next question says, name the actual force that provides the centripetal force in the following examples and state the direction of the force. A satellite in orbit of the Earth, an electron going around a nucleus, a cyclist going around the bend. Then calculate the linear speed of a particle just 20 centimeters from the center of a disk spinning at 6 radians per second. Then calculate the centripetal acceleration of the following objects. A car moving around a bend of radius 60 meters at a speed of 20 meters per second. A yo-yo swung in a circle with a radius of 30 centimeters at 5 radians per second, and an object moving in a circle of radius 1.5 meters with a period of 750 milliseconds. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, remember the centripetal force is the name given to the resultant force towards the center of the circle of the circular motion. So, the first one is going to be gravitational attraction towards the center of the circular motion. The second one is going to be electrostatic attraction towards the center of the circular motion. Then a cyclist going on the bend, that's the friction between the tire and the road, towards the center of the circular motion. Again, how can you link a linear speed to the angular velocity? Well, it is v equals r omega, so therefore you can say it's going to be 0.20 because you convert centimeters into meters times by 6 radians per second, so it's 1.2 meters per second. The next one, how can you work out centripetal acceleration? Well, centripetal acceleration equals v squared over r. So you can convert your values in and you get 6.7 meters per second squared. The next one, you can also use the equation A equals omega squared r. Again, it just depends on what values you give it in the question. So it's going to be 5 squared times by 0.60 because it's 60 centimeters into meters, so it's 15 meters per second squared. Now in this next one, you're given the time period. So when you're given the time period, you can then work out the angular velocity by saying omega equals 2 pi over t. We convert our milliseconds into seconds, so we get 8.4 radians per second. We then say A equals omega squared r to get out 110 meters per second squared. The next question says, a bicycle wheel rotates at 120 revolutions per minute. The radius of the bicycle wheel is 280 millimeters. Firstly, calculate the angular velocity of the bicycle wheel. Secondly, calculate the centripetal acceleration of the bicycle wheel. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you need to work out the angular velocity, and you can do so by converting your revolutions per minute into revolutions per second, and then you can then work it out by then using this idea of doing 2 pi over 60. So you can go 120 there, say, so times by 2 pi in general, sorry, so it'll be 2 pi, okay, over 60 times by 120 is therefore going to equal 4 pi radians, so you get a 12.57 radians per second. We can then use the equation A equals omega squared r to pop in the values. Remember the radius converts from millimeters into meters, so we get 44.216 meters per second squared. The next question says, the figure shows part of a track of a roller coaster ride in which a truck loops the loop. When the truck is at a position shown, there is no reaction force between the wheels of the truck and the track. The diameter of the loop in the track is 8.0 meters. Explain what provides the centripetal force to keep the truck moving in a circle. Then, given that the acceleration due to gravity, g, is 9.8 meters per second squared, calculate the speed of the truck. So pause the video now, then unpause the video when you want to go through your answer. Right, remember that the centripetal force is always the resultant force towards the centre of the circle. So when the truck is in the position as shown, the centripetal force must be acting downwards towards the centre of the circle. So the only downward force in this instance, because there's no reaction force, is going to be the weight of the truck. So therefore, how can we work out the value for the speed of the truck? Well, what we can say is that acceleration is equal to v squared over r, and we know the acceleration is going to be g, 9.8 meters per second squared, because the only thing accelerating it is gravity. So therefore we can rearrange it. We can make v the subject and say v squared equals rg. So therefore v equals the square root of rg, and it equals 6.3 meters per second. The next question says, a racing car of mass 1,200 kilograms travels around a bend with a radius of 140 meters. The maximum frictional force between the wheels and the track is 17 kilonewtons. Calculate the maximum speed at which the car can travel around the bend. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to remember that we're working out the centripetal force here. Because we know the mass of the car, we know the radius, and we know that the general equation for this is going to be F equals mv squared over r. Now we know what F is, it's 17 kilonewtons, so we convert that into newtons. We know m, which is 1,200, and we know the radius, which is 140. So we pop them all into the equation, we work it through, and we get 45 meters per second. We can use the equation F equals mv squared over r because it's going in a circular motion, and that must be the resultant force towards the centre of that circular motion. The next question says, on a ride of a theme park, riders are strapped into seats attached to the edge of a horizontal wheel of diameter 8.5 meters. The wheel rotates 15 times per minute. Calculate the force felt by the rider of mass 60.0 kilograms. Then, a car is being driven in a circle of radius 56.8 meters with a linear speed of 31.1 meters per second. Calculate the centripetal acceleration of the car. Then, the linear speed of the car decreases to half of its original value. If the original centripetal force experienced by the car was F, what is the new centripetal force experienced by the car in terms of F? Then, a biker rides in a vertical circle around the inside of a cylinder of radius 5.0 meters, so he's upside down at the top of the cylinder. For the biker not to fall off at the top of the loop, he must be going fast enough that his centripetal acceleration does not drop below the acceleration due to gravity. What is the minimum speed they must be travelling at the top of the loop? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to remember, what can you work out? Well, you can work out the frequencies. You can say it's 15 over 60 to work out that there's going to be 0.25 revolutions every second. You can then work out your angular speed. Now remember, angular speed or angular velocity, omega, is equal to 2 pi f. That's an equation you've got to be able to use. It is given to you in your exam. So now we've got f, we can work out the angular speed. So we've got 0.5 pi radians per second. At this point, we can use the centripetal force equation to work out the final force, because it's moving in a circular path. Now we can't use the equation F equals mv squared over r because we don't have v, but we do have omega. So we can use the other form of the equation where we say F equals m omega squared r, pop in all the values. Now remember, you're given the diameter in the question, not the radius, so you've got to half it, so therefore you get 630 newtons. This next question, we can use the equation centripetal acceleration is v squared over r, because we've got v and we've got r, so you pop in the values and we get 17.0 meters per second squared. Now, we'll see how the centripetal force changes in the next question. We know F equals mv squared over r. So therefore, if m and r are kept constant and v is halved, well, it's v squared. So therefore, the value of the centripetal force is quartered, so it's F over 4. Then finally, if the biker's speed is the minimum possible for him not to fall, then therefore our centripetal acceleration towards the top of the cylinder, towards the centre from the top, will be 9.81 meters per second squared. We know A equals v squared over r, so therefore we can work out what v is. So v would be the square root of a times by r, so it'd be square root of 9.81 times by 5, so it's about 7 meters per second. Let's now have a look at a few more contextual questions. So the first question says, by how many degrees does the angular displacement of the hour hand of a clock change each hour? Then a clock is shown 3.30 or 3:30. Calculate the angular displacements in degrees from 12, okay, the 12 position of the clock, to the minute hand and then the hour hand. And then convert the following angles from degrees to radians. 30 degrees, 90 degrees, 105 degrees. Convert these angles from radians to degrees. Half a degree, half a radian, 3/4 of a radian, pi radians, and pi over 2 radians. Then express the following angles as multiples of pi radians: 30 degrees, 120 degrees, 270 degrees, 720 degrees. So pause the video now, then unpause the video, and you'll want to go through your answer. Right, in this first one, you know that the full circular face of a clock will be 360 degrees. We know a clock face is divided into 12 sections because it goes from 12, okay, all the way back round again. So therefore it's 12 sections. So the angular displacement of the hour hand per hour is going to be 360 degrees divided by 12, which is 30 degrees. Now this next one, you would say the angular displacement of the minute hand is going to be half of the clock face, because as it goes from 12 to that particular, from 3:30 to 12, so we half the clock face, so it's 180 degrees. And for the hour hand, it's actually going to be 30 degrees, because it's going to be moving across like that, but it's going to be 3.5 hours of the 30 degrees, so therefore it's 105 degrees, because each hour gives you a 30-degree angular displacement or change, so therefore it's 3.5 hours, which is the difference, so it's 105 degrees. Again, to change from degrees into radians, you times your angle in degrees by pi over 180. So you're going to get 0.52 radians, 1.57 radians, 1.83 radians. To convert from radians to degrees, we will times by 180 over pi, or you could say divide by pi over 180. So you get 28.6 degrees, 43.0 degrees, and 180 degrees. Now, if you think about in terms of multiples of pi radians, well, 30 degrees is going to be 30 times by pi over 180, so it's pi over 6 radians. The next one 2 pi over 3, next one 3 pi over 2, then the last one 4 pi radians. The next question says, calculate the angular velocity of the Earth as it moves around the Sun. Then a hard disk spins at 4,500 revolutions per minute. Calculate the angular velocity and the time it takes to complete 50 revolutions. Then a spinning disk has an angular velocity of 565 radians per second. Calculate the frequency of rotation and the time taken to complete 5,400 revolutions. So pause the video now, then unpause the video, and you want to go through your answer. Right, in this first one, you've got to think about what the time will be for the time to go for the Earth to go around the Sun. And you've got to be in seconds. You do 365 times by 24 times by 60 times by 60. We then say angular velocity is 2 pi over t, as we looked at before. So it's 2 times by 10 to the minus 7 radians per second. Now the next question, we've got to convert our revolutions per minute into revolutions per second. So you divide it by 60 to get 75 revolutions per second. We then say pi equals, we say that omega equals 2 pi f. So therefore it's 2 pi times by that 75 is 470 radians per second. So to complete 50 revolutions, what you'll do is you'll do 50 times by the time period, which is 1 over the frequency. So it's 50 times by 1 over 75, 0.67 seconds. We can use the same methodology in this next question, but we can say f equals 2 pi over omega, because omega equals 2 pi f. So therefore we can say f equals 565 over 2 pi is 90 hertz. Then the time taken is 5,400 times by the time period, which is 1 over the frequency, so it's times by 1 over 90, which is 60 seconds. The next question says, explain why all the velocity arrows in the figure are drawn at the same length. Then, a toy train travels at a steady speed of 0.2 meters per second around a circular track. A and B are 2 points diametrically opposite to one another on the track. Determine the change in speed of the train as it travels from A to B, and then determine the change in the velocity of the train as it travels from A to B. Then show the angular velocity of the second hand of a clock is about 0.105 radians per second. Then, the drum of a washing machine spins at a rate of 1,200 revolutions per minute. Determine the number of revolutions per second of the drum and determine the angular velocity of the drum. So pause the video now, then unpause the video, and you want to go through your answer. Right, so in this first one, the magnet, they're all the same length because on the vector diagram, the length of the arrow shows you the magnitude of the vector. So the magnitude of the vector is remaining the same because the speed in circular motion stays constant. It's the direction that will change. Now in the next question, we know that the speed is a scalar and it's a constant value. So the change in speed from A to B, okay, is going to be 0 because you don't need to consider the direction. But in the second one, we do need to consider the direction. So because the object is changing directions, one of them has to be a negative value. So therefore it can be 0.2 minus 0.2, which is therefore adding it. So it's 0.4 meters per second for your change in velocity. Now this next question, we have looked at this before, but the second hand on a clock turns 360 degrees in 1 hour, so therefore, in 1 minute, sorry. So therefore it's 2 pi radians in 1 minute. So therefore it's 2 pi over 60 radians in 1 second. So therefore the angular velocity is going to be 2 pi divided by 60. So therefore it's 0.05 radians per second. In this next question, the revolutions per minute is 1,200. So you divide it by 60 to get in revolutions per second, which is 20. So our angular velocity, we know angular velocity is going to be omega, okay, which is 2 pi f. We know the frequency from before is the revolutions per second, so it's 20. So it's 2 pi times by 20, so it's 40 pi radians or 130 radians per second. The next question says, okay, that the angular velocity of the second hand of a clock is 0.05 radians per second. If the length of the hand is 1.8 centimeters, calculate the speed of the tip of the hand as it moves around. Then a car travels a 90-degree bend in 15 seconds. The radius of the bend is 50 meters. Determine the angular velocity of the car. Determine the speed of the car. Then a spacecraft orbits the Earth in a circular path of radius 7,000 kilometers from the center of the Earth at a speed of 7,800 meters per second. Determine its angular velocity. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to remember V equals omega r. So therefore, it's going to be 0.05 times by 1.8, and it's 0.19 centimeters per second. If you want to convert it to meters per second, convert the centimeters into meters. The next question says determine the angular velocity. Well, we know that the angular velocity is the change in angle over the change in time. Now, it's not a full revolution here, so we can say it's going to be 90 times by pi over 180. So we know that's going to be it's going to be pi over 2 radians, and then we're going to divide that then by 15 seconds, so it gets 0.05 radians per second. Then the speed is equal to omega r, so we multiply that by the radius, which is 50 meters, to get 5.2 meters per second. Now again, we can use this equation in the next one, and we can use this to work out angular velocity, because you know angular velocity therefore must be v over r. We convert the kilometers into meters, and therefore we get our answer to be 1.1 times 10 to the minus 3 radians per second. The next question says an object moves in a circular path of radius 30 centimeters with a velocity of 1.40 meters per second. Calculate the angular velocity and the centripetal acceleration of the object. Then a roller coaster designer creates a loop where the acceleration at the bottom of the loop is 5 times greater than the acceleration of free fall. The radius of the loop is 12 meters. Calculate the speed of the roller coaster required to provide such an acceleration. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know we can work out the angular velocity because we've got the linear velocity and we've got the radius of the circular motion. We've got to convert the centimeters into meters, so we get 4.7 radians per second. We can then work out our acceleration by doing v squared over r, so it's then going to be 1.40 squared over 0.30, 6.5 meters per second squared. In this next question, we can work out what the acceleration of our object must be. It must be 5 times greater than the acceleration due to gravity. So therefore you can work it out to be 49.1 meters per second squared. We know A equals v squared over r, so v equals the square root of AR. Pop in all the values and you get 24 meters per second. The next question says, show that in one revolution there are 2 pi radians. Then the figure below shows a centrifuge used to separate solid particles suspended in a liquid of lower density. The container is spun at a rate of 450 revolutions per minute. Calculate the angular velocity of the container. Then calculate the centripetal force on a particle of mass 20 milligrams at the end of the test tube. An alternate method of separating the particles from the liquid is to allow them to settle to the bottom of the stationary container under gravity. By comparing the forces involved, explain why a centrifuge is a more effective method of separating the mixture. So, pause the video now and unpause the video when you want to go through your answers. So, how do you answer this question? Well, the first one is you've got to think about what the situation is when you're doing one complete revolution. So that the angle in radians, like we said before, is the length of the arc divided by the radius. But the length of the arc must actually be the situation that's taken place. So therefore, the length of the arc must be the entire circumference in this case, because it's one complete circle. So that's 2 pi r. So therefore, we can say 2 pi r over r equals 2 pi. So the angle in radians of an entire revolution is 2 pi. Now in this next question, the angular velocity, we can say when we work it through is omega equals 2 pi f. That's an equation you've got to remember. So therefore you can work it through and you can pop in all the values. Remember, we convert revolutions per minute into revolutions per second, which is the frequency, by dividing by 60. So we multiply that by 2 pi and we get 56.5 radians per second. Now in this next question, f is equal to mr omega squared. We use that equation because we just worked out omega and we have r and we have m. Now note it's 20 milligrams. Now it's 20 times 10 to the minus 6 because the standard unit in physics is the kilograms. So to go from milligrams back into the standard unit, you've got to do 10 to the minus 6, not 10 to the minus 3. Pop in all the values and you get 6.4 times 10 to the minus 3 newtons. Now the next one, you can do this by looking at the value of the forces. So the weight of the object, which is the separation due to gravity, is going to be equal to 20 times 10 to the minus 6 there, times by 10, so therefore it's going to be 0.2 times 10 to the minus 3, which is much less than the required centripetal force. The next question says, in training, military pilots are given various tests. One tests put them in a seat on the end of a large arm which is spun around at high speed. Describe what the pilot will feel and relate this to the centripetal force. At top speed, the pilot will experience a centripetal force equivalent to 6 times his own weight. Calculate the speed of the pilot in this test, then calculate the number of revolutions of the pilot per minute, and then finally suggest why it is necessary for pilots to be able to withstand forces of this type. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you do this one? Well, the first one, you say the pilot would feel thrown out from the circle or pressured outwards against the seat, because the inertia means that there'd be no force. Okay, if there's no force in the situation, the pilot would want to travel in a straight line, but there's a centripetal force acting to pull them towards the center of the circle. So in the vertical plane, they'd have inertia, but in the horizontal plane, they'd be pressed in towards the center of the circle. So ultimately, that will cause a reaction to make the pilot feel pressured outwards against the seat. Now, to work out the speed of the pilot in the test, we can say, well, mv squared over r equals 6mg, because you know that is the centripetal force, and that's the equation for the centripetal force. So we can rearrange that and say v squared equals 6 times by rg. So we pop in all those values. Remember, g is 9.81, so we get 294. Then we square root that to get 17.2 meters per second. Now, the number of revolutions of the pilot per minute, well, we do omega equals v over r. We can therefore work it through to therefore equal 0.54 revolutions per second. Then to get into the minute, we can times it then by 60 if we would want. Now, the next question, why are they going to be able to stand forces of this type? Well, the sharp turns in combat mean at high speed would mean they'll experience very high g-forces when they're moving around like that, so they've got to be able to withstand them. The next question says, a car is travelling around a bend when it hits a patch of oil. The car slides off the road onto a grass verge. Explain, using your understanding of circular motion, why the car came off the road. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's happening is we know that the centripetal force in this case is the resultant force towards the centre of the circle. So that is the friction between the tyres and the road. Now therefore, if you've got oil on the road, you're going to reduce this value of frictional force. So therefore, the frictional force is not enough to push the car around in the desired curve. So therefore, it has to be in a wider arc because the value of F is lower. So therefore, it's going to hit the grass verge. The next question says, on one end of a string, it's secured to a ceiling and a metal ball of mass 50 grams is tied to the other end. The ball is initially at rest in the vertical position. The ball is raised to a vertical height of 70 centimeters. The ball is then released and it describes a circular arc as it passes through the vertical position. The length of the string is 1.50 meters. Ignoring the effects of air resistance, determine the speed of the ball as it passes through the vertical position. Then calculate the tension in the string when the string is vertical. Then explain why the answer to this is not equal to the weight of the ball. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to remember in terms of energies that, because we're not thinking of air resistance, we can say that the change in potential energy is going to equal the change in kinetic. Now I think I'm going to use this equation because I have values of G and of H and we want to work out V. So that's a really nice equation we can use because we can say, well, V equals the square root of 2GH when we cancel everything through. So you pop in all the values, we get 3.712 meters per second. Now we're trying to work out the tension in the string. Now you've got to think to yourself, well, what's the situation going on in this scenario? Well, we know the centripetal force, the resultant force towards the center of the swing, is going to be equal to mv squared over r. So you can work it through with all the information you've been given. You just worked out v in the previous question to get 0.548 newtons. Now what's the resultant force towards the center? Well, it's the tension, okay, which is going towards, okay, which is going to be going towards there, minus mg because it's going away from the center. So therefore T minus mg equals the centripetal force, which we just worked out. So therefore T equals the centripetal force plus mg, the weight. So therefore it's 0.95 newtons. Now why is this not equal to the weight of the ball? Because the weight is only equal to the tension when it's at rest in the vertical position, because at that point the only resultant force towards the center of the circle, the centripetal force, is going to be, okay, the weight. So the ball isn't in equilibrium in the vertical position because it's got an upward centripetal acceleration. The next question says, figure 17.20 shows an aeroplane banking to make a horizontal turn. The aeroplane is travelling at a speed of 75 meters per second and the radius of the turn in a circle is 80 meters. On the diagram, draw and label the forces acting on the aeroplane. Then calculate the angle which the aeroplane makes with the horizontal. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to think about what's the forces acting on this airplane as it's going in a circular motion. Well, we'll always have weight acting vertically downwards from the centre of mass, and you've got the lift force, which is going to be acting against the weight, but it'll be perpendicular to the wings because it's the wings that are helping produce the lift force, and those are the two forces acting on the aeroplane. Remember, the centripetal force is not an actual force, it's just the resultant composite acting towards the centre of the circle, so it doesn't have its own particular force arrow in this diagram. Now the next one, what we've got to do is, because it's at an angle, we've got to resolve the lift force horizontally and vertically. Because the lift force is at an angle, okay, we can't have it purely in the horizontal or purely in the vertical. So we know that vertically it's going to be L sine theta, and then its resultant force vertically will be the weight, so it'll be L sine theta equals mg. We can then say horizontally that the resultant force towards the center is the centripetal force, but the component of the lift force is going to be L cos theta, so L cos theta equals mv squared over r. Now we don't have the value of L in this equation, so we've got to cancel it through. So we can do the vertical equation divided by the horizontal equation. The L's will cancel through, and sine over cos becomes tan theta, a mathematical trigonometric identity you learn in GCSE maths. So therefore tan theta is going to equal 80 times by 9.8, which is going to be the radius times by the acceleration due to gravity, g. Then we divide it by the speed squared, so therefore we get 0.39. We inverse tan that to get 7.9 degrees. The next question says, explain what is meant by the term angular velocity. And then figure below shows a rubber bung of mass 200 grams on the end of a length of string being swung in a horizontal circle of radius 40 centimeters. The string makes an angle of 56 degrees with the vertical. Calculate the tension in the string, the angular velocity of the bung, and the time it takes to make one complete revolution. So pause the video now, then unpause the video when you want to go through your answer. Right, what do we know about this? So what is the angular velocity? Well, it's the angle covered or the displaced angle per unit time, but the angle has to be given in radians. Now, what's the tension? Well, if you notice here, we can see that vertically the tension, okay, is going to have, okay, a vertical component, and in this case it's going to be t cos theta, and that's going to equal the resultant vertical force, which is the weight of the object, because that's the only other force acting upon it. So therefore t cos theta equals mg. They equal each other because they're in equilibrium, because they're traveling at a constant velocity, so a constant speed. Okay, so therefore t equals 0.200 times 0.981 cos 56, which is 3.5 newtons. We know that horizontally, the resultant horizontal force, the resultant force towards the centre of the circle, is the centripetal force. That equals mv squared over r. So therefore t sine theta, which is 3.5 sine 56, is going to equal mv squared over r, or m omega squared r. So therefore we can work out omega. By looking it through, we can say it is 6 radians per second. So therefore, the time period is going to be 2 pi over the angular velocity, because angular velocity is 2 pi over t. So therefore, it's 2 pi over 1.04, which is therefore 1 second. The next question says, explain what is meant by the centripetal force. Then a teacher swings a bucket of water of mass 5.4 kilograms round in a vertical circle of diameter 1.8 meters. Calculate the minimum speed which the bucket must be swung at so the water remains in the bucket at the top of the circle. Then assuming the speed remains constant, what will the force on the teacher's hand be when the bucket is at the bottom of the circle? So pause the video now, then unpause the video when you want to go through your answer. As I said before, the centripetal force is the resultant force acting towards the centre of a circle on a body moving around that circle. It's a category we place forces into, it is not a force itself. This next one, we know that in this situation, when it's at the top of the circle, the resultant force towards the centre of the circle is the resultant force vertically downwards at that point. So therefore the centripetal force is equal to the weight. So we can say mv squared over r equals mg. The m's cancel through. V squared equals rg. So therefore v equals 3 meters per second. Then this next one, what will the force be? Well, the force is going to be equal to 2 mg, because at this point it's at the bottom of the circle. So not only do you have the tension acting downwards, but also you've got the force acting downwards. So therefore it's going to be double the weight. So it's 2 times by 5.4 times by 9.81, 106 newtons. The next question says, a model aeroplane moves in a horizontal circle. The path of the model aeroplane is a radius of r. The dots on the diagram represent 2 positions of the model aeroplane as it moves with a constant speed v. Derive the equation for the centripetal acceleration a equals v squared over r by considering the velocity of the model aeroplane at these 2 positions. Your answer should include a vector diagram. Then a model aeroplane is then attached to the wire. The wire is held by a person. The aeroplane moves in a horizontal circle of radius 28.5 meters at a speed of 22.5 meters per second. A lift force acts vertically upwards on the aeroplane. The lift force is equal to twice the weight of the aeroplane. The mass of the aeroplane is 1.55 kilograms. The wire will break if the tension is greater than 35 newtons. Deduce whether the wire will break. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to use the idea of the vector diagrams. So if you see this vector diagram here, we can look at that. We can make a triangle from the centre to A and then the centre to B, and then we can use that to work out values. So we can say that VA equals VB equals V, so it's a constant magnitude for that particular velocity. So therefore, with the small angle approximation, we can say the change in angle, the change in theta, is equal to change in V over V. Now we know that V is equal to omega t when we've worked it through. We can link it into omega, because we can say the angular velocity, omega, is equal to the change in angle over the change in time. So therefore the change in angle is equal to omega times by the change in time. So therefore the change in angle is equal to V change in time over r. So we've subbed in omega equals V over r. We can then rearrange it, and therefore we can link it through, as you can see on the screen. We can then cancel it through. Now remember, the change in velocity over the change in time is going to be acceleration. That's the definition of acceleration. So it's V squared over r. In this next question, we can say that the centripetal force equals mv squared over r. So it's 1.55 times by 22.5 squared over 28.5, so equals 27.5 newtons. Now we know the weight is going to be mg, so it's 15.2 newtons. So therefore the overall resultant is, when we use Pythagoras' theory, because we want to work out the resultant, which is going to be the tension, so it's going to be the square root of the centripetal force, k squared plus the weight squared. So for you work it through, it's 31.4 newtons, which is less than 35. You give your conclusion to your answer, so the wire will not break. The next question says, an aeroplane flies in a horizontal circular path while waiting to land at an airport. The aeroplane flies in a horizontal circle by tilt to one side in a movement called banking. The aeroplane creates an upwards lift force which acts in a direction perpendicular to its wings. The diagram shows this lift force when the aeroplane is banking. Explain how banking allows the aeroplane to fly with a horizontal circular path. Then during banking, the angle between the wings and the horizontal is 5.2 degrees. Calculate the radius of the circular path when the aeroplane flies at a constant speed of 530 meters per second. The mass of the aeroplane is 4.1 times 10 to the 5 kilograms. So pause the video now, then unpause the video when you want to go through your answer. Right, what you got to remember is the vertical component of lift will equal the weight of the aeroplane, because it's overall in equilibrium. So the two vertical forces will balance. So the vertical component of the resultant force is 0, because the aeroplane isn't accelerating vertically, it's not accelerating up or down vertically. So therefore it therefore means it'll remain flying horizontally. Now we know the horizontal component of the lift will act as a centripetal force. So the resultant force on the aeroplane is the horizontal. It's the only one that's left. So it acts as the centripetal force. So therefore, because you've got inertia in the vertical plane, you've got a resultant force towards the center of the circle in the horizontal plane, you will get circular motion. Now in this next question, we know that W is equal to mg, so 4.1 times by 10 to the 5 times by 9.81 equals 4.02 times 10 to the 6 newtons. That's the weight. Now we know that the vertical component of the lift is L cos theta, so therefore it is L cos 5.2, which is going to be 4.02 times 10 to the 6. So therefore what we can do is we can then work out values, because we can then also say that therefore we can say L is going to therefore be equal to 4.04 times 10 to the 6, because we can say L cos 5.2 equals mg, or the weight. So we can work out L via that method. We can then say, well, we know mv squared over r is going to equal to L sine 5.2, because that's in the horizontal. So therefore we can work out that the value for the centripetal force is going to equal to be 3.66 times 10 to the 5 newtons. We can then say, well, r is a factor we don't know about, but we know the value for F, and we know F equals mv squared over r. So therefore r is equal, and we rearrange everything, to 3.15 times 10 to the 5 meters. The next question says, a car travelled in a circular path as shown. A passenger in the car made the following claim. When the car was travelling at a high speed around a circular path, I was thrown outwards towards a force due to a force acting on me. The outwards force acting on me was the centrifugal force. Assess the claim made by the passenger. So pause the video now, then unpause the video when you want to go through your answer. Right, in how do you answer this one? Well, thinking about it, an application of Newton's first law to the path of the car or passenger, so if there's no force on the car or passenger, they'll continue in a straight line. So you need a force to change a resultant force to change the direction for the car or the passenger. So therefore, a force was exerted on the car towards the centre of the circle. This inwards force was exerted on the car at right angles to motion. So even though they were going, as you say, vertically upwards, it was acting horizontally. So therefore that is the definition of a centripetal force as well. It is a force that acts perpendicular to the motion of the object. This inwards force was exerted by the car and the passenger, so therefore there's not actually an outward force on the passenger. That's actually a misnomer of the situation. So there's no such thing as a centrifugal force. There's only an inwards force towards the centre of the circle, which is the centripetal force. So the centrifugal force is what we call a fictitious force. The next question says, the photograph shows children on a roundabout in the playground. The roundabout is a flat platform with bars. The children makes the platform rotate by running on the ground whilst pushing on the bars. It takes 12 seconds for the roundabout to make 2 complete rotations. A child is standing on the platform 1.8 meters from the centre of the roundabout. Calculate the speed of the child. So pause the video now, then unpause the video when you want to go through your answer. Right, you're told enough information to work out the angular velocity, because we know angular velocity is 2 pi over t. So it's 2 pi over 6, because remember there's 12 seconds for 2 complete rotations, so 6 seconds for 1 complete rotation, so it's 1.05 radians per second. We know v equals omega r, so therefore it's 1.89 meters per second. The next question says, a poi ball is a ball attached to a person's hand by a cord. A child makes the poi ball undergo circular motion in a vertical plane as shown in the photograph. The poi ball moves clockwise in a circle of radius r with a constant speed v. The diagram shows two positions a and b of the poi ball. Firstly, derive the equation for the centripetal acceleration a equals v squared over r by considering the velocity of the poi ball at these two positions. Your answer should include a vector diagram. The poi ball completes 1.3 revolutions per second. Calculate the acceleration of the poi ball. The radius of the circular motion is 0.58 meters. Then the child comments that as the ball goes around the circle with a constant speed, the size of the force on his hand changes. Discuss whether this comment is correct. So pause the video now, then unpause the video and you'll want to go through your answer. Like previously, you got to make a triangle from 0 to A and 0 to B and A to B. So you should draw this triangle out. You can then use a small angle approximation to say the change in angle is equal to the change in V over V. Remember, the small angle approximation takes away sine, cos and tan. So at that point, we can also say that, well, change in theta equals omega times by change in time, because omega equals change in time, change in theta over change in time. We can sub in that omega equals V over r, so we've got v and r in the equation. We then rearrange it, and we can then get delta, the change in velocity over the change in time as the subject. That is acceleration. So therefore, acceleration equals v squared over r. In this next question, we can say, right, well, v equals 2 pi f times by r. So we can say it's 2 pi times by 1.3 revolutions per second, because that is in fact the frequency, times it by the radius. You get 4.74 meters per second, and then a equals v squared over r. Pop in all the values, 38.7 meters per second. Now the child's claim is correct because the centripetal force is the force that he feels on his hand. Now we know that throughout this effect the tension is constant. Now the weight of the ball is added to the tension at the top because they're both acting towards the centre while they're at the top, but the weight is subtracted from the tension at the bottom because that's acting in the opposite direction to the centre of the circle at the bottom. So therefore the overall resultant force will vary, and the child is therefore correct because whilst the tension is constant, the resultant force is not. The next question says, if the Earth orbits the Sun in a circular path, and we've got 1 year is 3.2 times 10 to 7 seconds, the radius of orbit is 1.5 times 10 to 11 meters, and the mass of the Earth is 6 times 10 to 24 kilograms, calculate the angular velocity of the Earth, the linear speed of the Earth, and the centripetal force needed to keep the Earth in orbit around the Sun. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question we know omega equals 2 pi f, so therefore it's 2 pi over 3.2 times 10 to the 7, because remember it's 1 over the time period, so we get to 2.0 times 10 to the minus 7 radians per second. Linear speed is equal to omega r. We've just worked out omega, we multiply by r, and we get our answer out to be 29,000 meters per second. Then the next question, we're going to then look at the centripetal force, so F equals mv squared over r, the resultant centripetal force equation. You pop in all the values and you get 3.5 times 10 to 22 newtons. The next question says, a small object of mass 80 grams is attached to a string of length 1.2 meters swung in a vertical circle. It travels at a linear speed of 4.8 meters per second. Calculate the tension at the highest point and the tension at the lowest point. So pause the video now, then unpause the video when you want to go through your answers. Right, at the highest point, we know the following. We know that the resultant force towards the centre of the circle is the centripetal force, but it's also equal to the idea of T minus F. Okay, so we can say F is mv squared over r, so therefore we turn grams into kilograms by doing 10 to the minus 3. We then work it through and we get 1.536 newtons, but we know that the tension is equal to mg plus F, so therefore tension equals F minus mg, because F is the resultant force towards the centre of the circle, and mg, okay, is the weight of the object, and T is the tension. So when you do your diagram, it works through like that, so therefore it's going to be 0.75 newtons. Whilst at the lowest point, it's reversed. So actually now, whilst F is still the same, because it's still mv squared over r, and this centripetal force due to that is 1.536, we know that F equals T minus mg, because at the lowest point, we know that mg is acting in the opposite direction to the centre of the circle, so therefore it's a minus value, so therefore T equals F plus mg, so you add it, so therefore it's 2.3 newtons. The next question says, a light aircraft flying horizontally at 70 meters per second has a propeller of radius 0.5 meters, which makes 20 revolutions per second. Firstly, calculate the velocity of the tip of the propeller. Then when the propeller is at its highest point, calculate the force experienced by a 0.2 g mass attached to its tip, and then state what provides this force. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this first one, we know omega equals 2 pi f, and we've got f because it's revolutions per second. So we say, well, it equals 40 pi. We know v equals r omega, so therefore it's 0.5 times by 40 pi, which is 20 pi, which is 62.83 meters per second. Now, since the plane's moving forwards as the propeller is rotating, the two velocities, the horizontal and the vertical, are at right angles to each other. Okay, so therefore we combine using the Pythagorean theorem to find the resultant velocity. So therefore it's going to be r squared equals to 62.83 squared plus 70 squared, all square root is 94 meters per second. We then know f equals mv squared over r, so therefore we can pop all the values in and we get 1.58 newtons. What's this force? It's the resultant centripetal force towards the centre, okay, of there, so therefore the centripetal force, okay, is the gravitational force in this particular instance. So I hope you've enjoyed this particular revision session. If you've been successful and learned in today's lesson, you should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and understand what topics you need to improve upon for A-Level Physics in circular motion. So thank you so much for carrying out this revision session on circular motion for AQA A-Level Physics. Thank you so much and have a lovely day.